All the participants are requested to be seated. Warmest greetings and good morning to everyone. Welcome back to second day of NEST 2025, the National Symposium on Nuclear Energy for a Sustainable Tomorrow. Hope you all had an enriching and engaging first day. We have another exciting day planned, filled with insightful talks and discussions. To begin our proceedings, we move directly into session 4, which focuses on accelerator technologies and nuclear medicine. First speaker of the session, Sree Kandre, Head, Radio Pharmacy Section, Radiation Medicine Center, BAG, Tata Memorial Hospital, Mumbai, speaks on radiopharmaceuticals in medicinal diagnostics and therapy, societal benefits, followed by Sri R.I. Bhatt Singh, Head, Accelerator and Pulse Power Division, BAR, on particle accelerators and their applications, followed by K.N.S. Nair, ex-Chief Design Engineer and Head Technology Development Division, BARC, retired, and Director of Facilities Management, Molecular Cyclotron Private Limited, speaks on experience of setting up a medicinal cyclotron facility in Kerala. The session is chaired by Dr. K.V. Das, Vice President ERA, and co-chaired by Dr. Santosh P.P., Head Department of Zoology, Sree Krishna College.
Very good morning to one another. Myself, Dr. Santosh, Associate Professor, Department of Zoology, Sree Krishna College, Guruvayu. I'm very happy to be here. You are the postgraduate and Department of Physics Research Center now coordinating a national seminar on atomic energy and Indian Nuclear Society, nuclear energy for sustainable tomorrow. First of all, I express my thanks to the coordinator, Dr. Vishnu sir. He invited me to introduce our resource person. I asked him how I am, sir. None of the biology is a soul heart with the physics. Because any biological events are coming from the cortex of the physics. I know that because we are using microscope every time. The physical application is going on there, and we have a paper on physics during the PG time, biophysics. So I'm very happy to be here. I'm going to my duty. First of all, I giving a brief introduction to our chairperson here, K. Venugopal Das sir. He from Trivandrum and worked in fellow for 4 years, and he joined in BARC in 1973. He was on fuel reprocessing group of BARC and section head of the instrumentation, looking after the nuclear instrumentation and data processing. Later, he transferred to Mumbai and he retired on 2002 as a senior scientific officer, stock engineer. Here, sir, I welcome to be the chair. Thank you. On behalf of the Department of Physics and Sree Krishna College, Guruvayur, I extend my sincere thanks to you. And then the first session is going on. Accelerator technologies and nuclear medicines. Sri Muktagand Ray. I extend my privilege to introduce him. He is a scientific officer and head hospital radio pharmacy section RMC, affiliated to Baba Atomic Research Center, and he has 27 years of experience in this area, and his area of interest is automation of Erythrium-90 dotted synthesis and scaling up preparation process to meet the clinic requirements, formulation new radiopharmaceuticals with GA68 and LU-177 radio tracer and radio respiratory application in drug sustainability studies, radio immunoassay. His major achievements include DAE Group Achievements Award 2018, supply and clinical assessment of Lutetium-177 dotted based radiopharmaceuticals, and he has published a number of papers with more than 15. On behalf of the Physics Department of Postgraduate Department of Physics and Sree Krishna College, Guruvayur, I boldly invite and welcomes to you, sir, to the presentation.
Before that, I would like to say a few things. This session was originally for 1.5 hours. We started late by around 30 minutes. Still we have got enough time, so we can take around 25 minutes each speaker. 3 speakers are there in this session. I think that would suffice.
Okay. Thank you, Chairman. Do not worry, I'll stick to my time, maybe less time. And thank you for the nice introduction from my friend over here. I heard he's from Department of Zoology. So he was debating that how fit he is over here. But I graduated from MSc Botany. So since I am fitting over here, you will also be fitting over here. We all in biology have read one book on Leninger. The first chapter says that cell obeys the laws of physics and chemistry. So everything is about physics and chemistry only. Can I have my first slide, please? Yesterday, we had an interesting talk on nuclear energy and its applications, safety aspects. And let us recollect what are the things we read or we came to know about it. And my lecture is oriented towards the students over here. So most of you have, we had the first few lectures on safety aspects of nuclear energy and what is our ignorance about radiation. Then we also talked about isotopes from the nuclear waste. So I'll be highlighting one of the isotopes which we are using from the nuclear waste and also something about the threshold. So before I start my talk, I just want to show this slide. You must be very familiar during our school days with spot the difference, right? So can you spot the difference between these two pictures? One picture which is in green border and another red border. Can you note some difference? If you see over here, this picture is actually sections of your heart. Your heart, the heart is actually sliced into many slices, and that sliced around 16-20 slices, longitudinal, horizontal, and axial slides are seen over here. Now, if you see in the left-hand side with green color, this is a normal scan. Okay, this is a normal scan, and this is a scan where there is an issue, there is a myocardial pathology over there. Therefore, you see that there is a difference in the diagram. If you look over there, the distribution of this colored circle, it is somewhere you see this is discontinued over here. You see, it is not fully complete. It is just a C shape over here. So some pressure over there is missing. Okay. Where this is fully, you see the full, you can see the full lesion over full, it's highlighted. So this is the beauty of using radiopharmaceuticals in scanning of your heart. Now look over here. Now here, this you see is the kidney. I don't have pointer over here. So this is the kidney over there, and there is a bladder. There are two kidney and the bladder over there. So what's happening over here is that the radiopharmaceutical is injected over there. It goes to the kidney, and then it comes to the bladder. Okay? So this is normally when you drink water, okay? The water will absorb, and then it goes to kidney, and then goes to the bladder. That is normal. From the left hand side, here this is the issue over here, that the radio injection is being retained by one of the kidney, it is not coming down. The retention time is delayed. So therefore, there is some issue with this particular patient in clearance of your kidney. So there is some obstruction, probably there is some obstruction. And this is especially useful when a baby is crying. When you are having a difficulty, you can say, Doctor, I am having pain over here, I am pain over there. But a baby just cries. Usually in our center, a lot of pediatric patients, or babies from 1 month to 10 months, they are referred over here. And especially they have an issue, when they have an issue with renal problem, then you have this kind of pathology, where look for some obstruction. This obstruction can be because of infection, or it can be because of stones. So this is a normal DTP scan, and this is a scan where it's showing an flow clearance. So my title of the talk is Radiopharmaceuticals in Medical Diagnosis and Therapy, and I am from Radiation Medicine Center, BRC. And we are using all the radioisotopes that are produced in the nuclear reactor, and these radioisotopes, which are usually short-lived isotopes or medical useful isotopes, are brought over here, and you conjugate that with suitable pharmaceutical to make it a potent radiopharmaceutical. So this tracer technique was invented by George Hersey in 1913 in biology, and he proved that the amount of radiation required for such studies is so small the system under study need not be affected. So the concept and initiation Radiation Center has come through a vision Dr. Homi Bhabha, with the aim of useful use of nuclear energy for mankind through its medical and biological applications. This is a radiopharmacy in DA over here. So on the left hand side is a Durga reactor where usually a radioisotopes, all medical useful radioisotopes produced over there. It is processed in the radiopharmaceutical division of BRC under the isotope program of BRC. It is from there, it is taken over to BRIT, that is a board of radiation isotope technology. There are sister department which is responsible for distributing these radioisotopes in clinical form to various nuclear medicine centers in India and to RMC also. So it finally comes to Radiation Medicine Center. This is our hospital, which is located inside Tata Memorial Hospital of Parel. Now, what is a radiopharmaceutical? So, it's a pharmaceutical which is bind to radionuclide, and usually it is used for radioactive compound, which is for diagnosis and therapeutic treatment. And in nuclear medicine, nearly 95% of radiopharmaceuticals are used for diagnostic purpose, while the rest are used for therapeutic treatment. Radiopharmaceutical usually have minimal pharmacological effect. For example, if you are having a crocin, the moment you will take a crocin, it is intended to reduce your inflammation. So this is also a pharmaceutical. It is not to make any effect. So there is no major pharmacological effect of the pharmaceutical part. The only thing is that whatever effect you may feel, it is because of radioisotopes. Now, whenever a radiopharmaceutical is used for therapy, there the dosage of pharmaceutical can be higher side, so some amount of pharmacological effect might be there. Now, this is a time scale which tells the development of nuclear medicine and radiopharmaceutical. So it started from 1923, and with the coming up of iodine and we started the first nuclear medicine imaging process, where the iodine, especially sodium iodide, it concentrated in the thyroid gland. So thyroid imaging studies and all thyroid-related disorder studies was possible because of development of iodine 131 and iodine 125. Then gradually you see this is where the technetium started, and in 1975 we started FDG, and over here if you look this, because this slide I have borrowed it from a Western lab, what is missing over here is that between 1975 and 2011 you see this PSM lab. Actually in BRC in 2009 we already started lutetium rotated therapy. It already started, but it was not started anywhere part of the world because they were still waiting for FDA approval. So if you have you heard of Steve, who died of neuroendocrine tumor, had he come to India, he could have probably got treated over there. Lutetium rotated got FDA approval in US in 2016, whereas in BRC we have already in RMC started treatment since 2009. And that is only possible because of our help from a reactor. This is a cartoon which again shows the chemical composition of radiopharmaceutical, where we have, if you look over here, that arrow, that brown color figure is a pharmaceutical, and the yellow symbol over the radioisotope. They are tagged, and once that is tagged over there, you have that is potent radiopharmaceutical. It goes and targets one of the receptors in the cell. So you have two types of radiopharmaceuticals. One is diagnostic and another is therapeutic. And for the diagnostic, they are broadly classified again into PET and SPECT radiopharmaceuticals. PET stands for positron emission tomography, and SPECT stands for single photon emission computed tomography. And usually PET isotopes are fluorine-18 and gallium-68. They are very short-lived isotopes. And fluorine-18s they are produced from our medical cyclotron facility. Just for your knowledge, let me inform you. The first medical cyclotron in India was installed at RMC in 2002. And after that, there are 23 to 24 installations all over India. And we are also a training center for doctors and technologists for training them in nuclear medicine. And you will find the alumni of RMC around the entire country in various nuclear medicine centers. This is a list of radioisotopes which are used in nuclear medicine and the corresponding energy range. And if you look at the half-life, it is ranging from 6 hours to maximum 8 days. So these are short-lived isotopes. Usually all diagnostic isotopes have a half-life of around maximum 2 hours to 6 hours. Gallium-68 is around 68 minutes. Whereas therapeutic isotopes have half-life from 6 days to 8 days. Whenever we were discussing radiopharmaceutical, yesterday we discussed about, somebody was mentioning biological half-life and the physical half-life. So here, the physical half-life is the half-life of the isotope. But the moment the radioisotope is injected in the body tries to eliminate that. So that becomes biological half-life. So usually what happens for technetium with a half-life is 6 hours. But moment is injected to the patient, it is excreted within 1 hour. So the biological half-life is still less than 1 hour. Okay, this is one slide which tells a very fundamental difference. What is ideal SPECT radiopharmaceutical? that if you look at all radioisotopes, they decay by various modes. One is either they emit a alpha, beta, or a gamma photon. Usually, all diagnostic radiopharmaceuticals are desired to emit a gamma or X-ray photon, not any particle emission. Particle emission like beta or alpha, they will harm the body cell or they will interact with the body cell. Usually, all diagnostic radiopharmaceuticals are ideally like technetium, the pure gamma emitters. Whereas therapeutic pharmaceuticals, they prefer to have a beta component so that they will kill the cancer. Second interesting part of spectral radiopharmaceutics is the contrast. For example, when they should be able to localize, and normally whenever a radioisotope is injected, if you immediately take a photo of the patient, the entire body will brighten because all the isotopes are evenly distributed throughout the body. But after half an hour, they will concentrate in the actual place of, for example, they are supposed to go to kidney, all the isotope will concentrate in the kidney. So, there you call as, what you call over here is that target to the target organ and the outside ratio. Okay. Non-target, target to non-target ratio, where target to non-target ratio should be more than 98%. Okay, so when you're talking of designing of radiopharmaceuticals, though this was not required over here, just the important information whenever we are thinking of designing radiopharmaceuticals, the first picture comes when what is the target organ. And once you think target organ, we try to find out what receptors are present target organ, which is not present in any other organs of the body. So then it becomes easier for us to find a ligand which will bind to this target tissue, and then we will find a way to radiolabel this ligand. Okay, so same thing, whatever I told you just now. Now these are the radiolabeling methods. So those who are from chemistry, they might try to come to know that what are the radiolabeling methods we have available for radiolabeling a radioisotope with a ligand. So it's a simple chemistry. Either it is an isotope exchange. When you talk isotope exchange means, for example, thyroid hormone. Your thyroid hormone is there. Thyroid hormone biologically has 4 iodine atoms. Whatever thyroid hormone like thyroxine or 4-TSH, just like thyroid gland, they have 4 iodine atoms. So I can do an isotope exchange. If I want to radiolabel thyroid hormone, I can remove 1 iodine and I can replace that with radioiodine part, like 131 or iodine 1. So it is possible. And it is very simple. Oxidation reduction reaction is possible. You can do that and you do it in our lab. So similarly, there are various ways of doing. For example, let us say you don't have any suitable isotope exchange. Then you can use a bifunctional agent. For example, some agents, they act as chelators. One arm, they will bind to the radioisotope, other arm, they will bind to a ligand. So these are called as bifunctional chelators. What are the factors related to radiolabeling? A higher labeling yield is desirable, that is obvious. So whenever you are doing a labeling method, you expect that whatever radioisotopes are there, they will at least label to your ligand more than 90%. So in case of diagnostic radiopharmaceutical, 90% is preferred. To therapeutic, 95% is preferred. Then specific activity is also desirable. Then radiolysis. Radiolysis situation is that after you radiolabel your product, because of the radiation that induced the radioisotope, that can damage the product. So that can cause radiolysis. So we have suitable agents, some kind of chelating agents are added or some kind of, what you call that, free radical scavengers are added over there to make the product stable. Then storage conditions. Sometimes storing in ice conditions will increase the longevity of the isotopes. And for example, BRIT, they supply tagged radiopharmaceuticals from Mumbai to Delhi in dry ice. So the isotopes are quite stable in. A little bit of technetium. See, technetium is not a natural element. It is a man-made element. It is not found naturally. Okay, it is from molybdenum. So this, and technetium happens to the workhorse of nuclear medicine because 80% of of radiopharmaceuticals, the used in nuclear medicines, they are all technetium based. So usually it is convenient to use the technetium because they are supplied in a moly-technetium generator. So what you see, this is a generator. It is not like generator for electricity. We call this a chemical generator. So inside you have moly 99, which is half-life of 36 hours. So what we do is that every day morning we elute like a cow, milking the cow. We milk the generator. So we put saline over there and then we elute out the technetium out. So daily. So for any nuclear center, these generators are delivered and Saturday, Sunday, Monday morning we start eluting. Monday to Friday we elute the generator, and Monday we may get 1,000 millicurie of activity. Tuesday we get 700. Wednesday we get 600. And Thursday we may get 400. Friday 300. So this is how it falls over there. But it is sufficient for our diagnostic to take care of a patient. And this is a cross-section generator you see over here. This is the core over there. The moly is trapped in the column over here. And in the yellow part you see you put the saline over there. And here we put evacuated vial. So because of vacuum, it pulls the saline to the column. And the moment wherever in the column moly is liquid technetium 99, that technically is stripped from the column and taken up of there. That is how you elute this technetium by a very simple way. And then what we have is cold kits. Again, these cold kits are marketed by Blade Component. Cold kits is nothing. They are pharmaceutical and reducing agent. You just add a technetium in the kit over there, and your pharmacy ready. You must have seen your penicillin injection or ampicillin injection taken. What doctor do is that he takes the vial and he puts saline or water, shakes it, takes it out and takes it. Same way. Here you take the vial, take the technetium which is saline, put in the vial, take it and let you use. So, but this is how we prepare radiopharmaceuticals. It is prepared in special wood. We take proper precaution because first of all is that we have to protect ourselves. Because the radioisotopes, we have to protect ourselves first. Second thing is because it is injured patient, it has to be in a sterile zone. So we have to protect the specimen also. So both ways it is very stringent. And after that, we do a quality control. We want to ensure that whatever we prepare is more than 90% efficient. So therefore that we need to do a TLC. So this is the quality assurance of radiopharmaceuticals. So we go for the physiochemical quality control, this clarity, we look at this clear solution, then radiochemical purity, the pH, then the biological quality control, that is, there should not be any practical endotoxin. So these are some of the technetium radiopharmaceuticals which we prepare routinely in a lab, depending upon the patient load. So if you look over here is that we have listed the radiopharmaceuticals, okay, and for what purpose they are used. Anyway, the slides are here. Those who are interested to it, they can always take the slides. And this is a cartoon which shows that what are the maximum organs in the body we can do by SPECT imaging. Whichever part you want, we have an agent. This is a slide about the PET radiopharmaceuticals. We kind of PET radioisotope like 11 carbon, then 15 oxygen, nitrogen 15, fluorine 18, gallium 68, and rubidium 82. These are some of the PET isotopes. This is the half-life and how they are produced in the nuclear medicine facility. In RMC, we routinely produce fluorine 18 through cyclotron and gallium 68 through a gallium generator. Some of targeted therapy. Nowadays is that the cancer, when you talk of cancer therapy, one is cancer therapy, other is targeted cancer therapy. So what is cancer therapy? Is that whenever a patient undergoes a cancer therapy, there are two options. One is that if the cancer is localized, then doctor will prefer to surgically remove the cancer. So that is one way of, that is the best way, surgically remove it and you have curable cancer. Suppose the cancer spread to other parts of the body. Then the doctor decides a combination of radiation therapy or a chemotherapy or a surgery. So in chemotherapy, the drugs that are used, they are targeting the dividing cells. Cancer is a dividing cell which is dividing rapidly. So whenever you are giving a drug of dividing cells, in your body there are many normal cells like hair root of the hairs, skin cells. They are also in dividing states. So those cells are also affected. That is called the side effect of chemotherapy. When I am talking of targeted therapy, which is possible radioisotopes, where we design, for example, neuroendocrine tumors, which are present in pancreas or any other part, they have a receptor called a somatostatin. This somatostatin receptor is only specific to neuroendocrine, and we want to kill them. So what we do is that we take somatostatin ligands which can bind to somatostatin receptor, which is rotated. So what we do is that in this rotated, we tag radioisotope and then we inject that in the patient. So the rotated will take the radioisotope along with that and to the neuroendocrine tumor cells. It will bind over there, the isotope is sitting over there, so when the isotope decay, it will replace the energy of the decay to the cancer cell and the cancer cells will eliminate. That is called a targeted cancer therapy. So this is what we are talking about over here. This is the radioisotope, and you an orange color is a pocket arm which will capture over there. The other arm is in the operator pad which is specific for the tumor. So these are the bidentate ligands. So this is how you see the lutetium is, labeled by the rota. Okay. This is a repeat slide. So these are some of the tables we show in our center where we've been using these various therapeutic radionuclides, and this is kind of therapy we do over there. And this is just for your thought that yesterday you were talking about uranium. How from uranium chain we are getting this actinium-225 for our patient use. And these are some of the number of cases we have been handling data center. And this is our senior Dr. Norana who started radiopharmacy to RNC. And these are then Dr. Rajan, who again took the radiopharmacy to the next level. Then followed by Dr. Samila Banerjee. Now myself heading this section. And thank you very much for your attention.
Thank you, sir. Now it's time to express our gratitude. So,
One second. Is there any questions on this subject? We can have one or two questions.
One hand is where.
I am not asking any questions. No.
You are saying I could.
How it is for 82 second half-life.
82 seconds after.
So how do you manage that?
Some isotopes which is very short half-life, there what happens that it is directly delivered from the cyclotron to the patient through a tubing channel. And that is only possible for only few isotopes, not for all isotopes.
This is being used 82 second rubidium. Sorry, that.
We had a system at our center but we never used. But it is possible.
I have a request to you. The courses in RMC, what you offer for students, what is the qualification required and what is that, if you can tell them, some may be interested.
We have an MSc, two MSc course, MSc Nuclear Medicine Technology and Molecular Imaging, and another MSc Nuclear Medicine Technology in Hospital Radiopharmacy. So for both these courses, your eligibility is BSc with physics, chemistry, with BSc physics or chemistry. It is advertised in the nuclear, in many newspapers. even BSc botany zoology also they can also apply. And this particular course is 2-year course, and it has a stipend also. Students who are selected, they get a stipend of 18,000 rupees per month, and hostel facility is also available. And our intake is maximum 10 patients for each course. So total 20 students can be taken in 1 year for both these. And after the course, you are eligible to work in veterinary centers in veterinary technology. There is an entrance examination, there is a common entrance examination, and you will be asked to answer 150 multiple choice questions, 50 from physics, 50 from chemistry, 50 from biology or maths. Sample paper is there, then provide to you on request. It is physics, BSc physics, chemistry, botany, zoology, and then microbiology. And for hospital pharmacy, bachelor in pharmacology also, pharmacy also, they can also apply, or BS technology, they can also. If interested, I can value the detail over there. Quarter percentage, they have to score minimum 50% in entrance exam, and usually our cutoff for last 2 years, so who have scored about 780 marks, 760.
Sir,
So it is first top 10.
sir, is there a risk of harming actually healthy cells during the radiation therapy that is targeted? Can healthy cells be accidentally harmed during the radiation therapy?
It is like this, so if there is an lathi charge, the police which is starting to drive off the way. So you standing there and the onlooker, you may also get a chance to get hit. So that is called a bystander cell effect. That is, whoever cells are nearby, they also get affected.
Hello. If that is all, I thank Mr. Ray for a wonderful talk. Thank you so much.
Thank you, sir. Now it's time to express our gratitude. So I would like to invite Dr. K.V. Das to present a memento and a book titled On Wheels of Education, Serving USA and India, written by Professor Sree Krishna, a renowned scientist to Sri Muktaganra. Thank you, sir.
Hello. Next session is, our talk is by R.I. Bhakti Singh on particle accelerators and their applications. I invite Mr. Bhakti Singh.
Please be seated, sir. Here I am taking my another privilege to introduce our resource person of the second session, Sri R.I. Bhakti Singh. He is now delivering a speech on particle accelerator and their application. At present, he is working as head of accelerator, pulse and power division, BART, Mumbai. He did his master degree in electronics and communication engineering from Anna University, Chennai, and joined accelerator and pulse power division, BART in 1994. After completing third batch OCEP in BART Training School. He has been involved in the design and development of high voltage, high frequency power sources for electron beam accelerator. He has 30 years of experience in the indigenous development of DC and RF accelerator for various industrial and societal applications. The accelerator were demonstrated for water cleaning, power semiconductors, agriculture products, cargo scanning, neutron generator, etc. He has participated in the testing of superconducting magnets in Large Hadron Collider, CERN Geneva in 2006. He is recipient of BAE Group of Achievement Award for DC Accelerator 2030 and currently holding the cabinet post in Power Beam Society of India. He is heading the Accelerator of Pulse Power Division from 2021 onwards. He has contributed more than 50 publications including journals and conferences. On behalf of you and the Department of Physics, Sree Krishna College, Guruvayur, I cordially invite you, sir, to deliver the speech. Thank you.
Thank you. Good morning, everyone. And I first of all thank the NEST 25 Organizing Committee for giving an opportunity to come to Sree Krishna College. Yesterday night I happened to get greeted by the hotel managing person. His name also Krishna. And I inquired him, I have come for Sree Krishna College. He told I had passed out from Sree Krishna College only. And after that I did my management, hotel management and joined. So I was very glad to visit your place, Guruvayur, and to be with you all today. So I would like to take this session as an interactive session. So I may be asking some questions to you. If you can also ask questions, it is good. We are representing Department of Atomic Energy and Baba Atomic Research Center. In both of these things, a common word is there. What is the word? Department of Atomic Energy, Baba Atomic Research Center. Atom. Okay. So what is the size of an atom? Have you ever seen an atom in your life? Anybody can answer. Have you seen atom in your life? If you have not seen. Why we have not seen? What is the size of an atom? Anybody can answer. No, not you. Even for the students. 10 power minus 10 meters, that is Einstein. So you be alert and then, because you are coming from physics, and our hair size thickness is about microns, 10 to 50 micron thickness, okay? And we are working in the atom. Atom is revolving and electrons are revolving around the atom. Neutrons and protons are inside the nucleus. So we take out the electron, proton or neutron and how we can use for peaceful purposes, energy, for various industrial, societal, medical, other applications. The first lecture was started with radio pharmaceuticals. So I will be going through particle accelerators and their applications. Next slide. So what is a particle accelerator? The word, when you hear accelerate, what do you think? Where do we accelerate? Accelerate means what? To speed up. Bike, if you give an acceleration, it goes in a speed. And in a chemical process, if you give some catalyst, it will accelerate the process. And in various applications, we accelerate. We want to accelerate things very fast. We want fast food many times, not slow food. So this accelerate, what we mean here, particle accelerator. We can accelerate the particles and charged particles in particular. Okay, so as you have seen, we cannot see the atom and we cannot see the electron also. So how we can take out the electron or proton or neutron and accelerate? Size of atom is 10 power minus 10. Electron will be 10 power minus 14 or minus 15 meters. So how we can take out the atom, this electron? So if you see some of the tungsten bulb, earlier times we were using tungsten bulb. which is giving light, heat, and then electron also. Many of the people, we may not be knowing aware, tungsten bulb gives out electron. If you are heating any material or metal, beyond its work function, in physics you will be knowing, beyond the work function, it will start emitting electrons. Electrons, blue color, red color, yellow color, which color it will be? Red color you like? You cannot see first of all. We can see, sense only the air thickness, 20, 50 micron. If it comes in our mouth, we can sense. But the electron, we cannot sense. But I have to accelerate the electron. How I can do it? So that can be you can see a small illustration. If you heat tungsten, the terminal cathode is written there. That you call it tungsten or you use any metal. If you heat it, it will start emitting electron. But this tungsten bulb, why we are not able to take out the electron? They are again recombining in the air and then get lost. So if you have to accelerate, we need a potential DC. So you can see that E equals V by D. Okay. How much voltage you are giving between two plates, capacitor plate, that much energy you can give to the electron. So in a gun or anything, bullet, we give a kick and then that goes in the speed of 1 kilometers per second or more. And ballistic missiles are going supersonic speeds. Okay. But what is the speed we want to accelerate the electrons? What is the speed? What is the speed of light? Anybody can answer. Speed of light? 3 into 10 power 8 meters per second. Can we travel the speed of light? What will happen? If we are able to see the atoms, if we are able to see electrons, protons, we cannot move any one step ahead. If a cloud or fog is there in front of us, will we move? Any car or anything can be done? Nothing. So God has made us with visible eyes, so that whatever we want to see, that much only is allowed for us. Electron cannot be seen, but it can be produced by thermionic emission, photo emission, or field emission. Okay. There are three methods. Electrons can be emitted. Similarly, this is a negatively charged particle and positively charged particle. If you want proton, you split hydrogen H plus, then we get a proton, and that can be accelerated by the voltage. And how much voltage you give, that much will acquire energy. 1 kilovolt, 1 million volt, 1 gigavolt, 1 teravolt, you can increase. Can anyone, have you seen high voltage in your life? I was first to say, have you seen atom? Yes, we have seen atom and sensed. Our body is made of atoms. It is not somewhere else. Atom means we are thinking uranium or some heavy metal. But atom is there everywhere. The air also atom is there. Okay. So I am making it very light. So we are working with atomic energy research, and we are taking out the electron and feeding it. And once it is going the speed of light, beyond 500 kilovolt, electron acquires the speed of light. And with the speed of light, when charged particle is moving and hitting, what will happen? I'm sorry. Bhaskar sir is seated to me, and so I can hit it. So if electron is hitting at the speed of light, what will happen? That's why is so tiny, it can interact with so tiny things only. It can break the covalent bonds, it can ionize the atom, it can deal with the atomic level only. Kindly give me some time, it will be interactive, and so that you may get some interest into the subject. Okay. So, this electron, very tiny thing, can interact with atomic level or molecular level. It can ionize the atom, or it can dissociate the molecules. I have worked around with Bhaskaran sir. So that's why I'm taking his name again and again. So whatever the air we are having, this room, we have, what are the things we are having? What are the air molecules we are having? Oxygen, nitrogen, let everyone come out, come on. Oxygen, nitrogen only is there, nothing else. Carbon dioxide, then argon, helium, etc., small quantities, okay? And else, what else? Huh? Dust particles are there, what else? We have dealt with the flue gas, okay? We have got moisture, H2O in the air, okay? So these are all very basic things, but many times in our practical life we don't realize. So if electron goes through this air, it will recombine and get lost. So we need a high vacuum, okay? We need a high energy, we need high voltage, we need high vacuum, and then I will come to further things. We need high frequency, we need superconductivity, many things, high things are needed. So we are many times involved in interacting with high voltage, but we are not aware. In your home, everybody, none of us are left out. We are using the gas lighter. What is the principle it is working through? Do you know? Anybody can tell. We are daily using that gas lighter to switch on our gas. Yes. No, that is okay. In the gas lighter, what is happening? Spark. How the spark is made? What are you doing? What are you doing? You are doing some job. You are giving a kick. I'm sorry, I am not kicking you. You are giving a kick. Basically, we are giving a kick to something inside. What is the kick we are giving? To whom? That is a piezoelectric crystal. Have you heard of that? Anyone? That is a piezoelectric effect. To give a kick to piezoelectric crystal, it will produce voltage and there is a current. So, this is applied between spark gap. The terminals you are seeing, we are generating about 1 kilovolt. 1000 volt we are generating. And we are giving a kick. Mechanical energy is translated to electrical and that is spark. Okay? But some places we want to make spark and some places we don't want to make spark. Sometimes we want to make noise. If students, if you tell you make noise, it is very huge voice you can raise. But keep silent means very difficult. Okay? So some places we have to make spark to ignite. Okay? And some place we should not take spark. And that is our accelerator. Inside the accelerator we don't want to make any spark. High voltage is there. We are generating kilovolts, 500 kilovolts, 1000 kilovolts. I will come to that slides. So, we are generating high voltage. We have to accelerate this electron and these electrons ionize the atom and they can dissociate the H2O molecules in the air or in the water and they produce some OH radicals which can react with the pollutants. This can produce ammonium sulfate, ammonium nitrate. We have made in our electron beam center, I will come to that. And then we can clean the water. Okay, instantaneously we can do. So, now let us come back again. We are dealing with atom. Atom is having proton, neutron inside nucleus, and then electron is revolving outside. We have not seen. Somebody, scientists have told, yes, it is there. Oxy, yes, sir. We are believing and we are sensing it. We are using it in our everyday life, high voltage, and then we are using mosquito racket, we see that is producing high voltage, and that is also useful. Okay, and the spark is made in your bike, scooter, car, everywhere. Okay, so high voltage is needed, and in making spark, and to accelerate the charged particles also. And once it is charged and accelerated, then you can use it inside vacuum or take it out and you can process. So for example, we are having these cables here. These cables, if it is continuously vibrating, it will make wear and tear. The aircraft cables, and then traction, train, and so many things. And in the house also, whatever cables we are using, they are all cross-linked. So this can be made by electron beam. Clean environment, we can do it. And we can give colors to the diamonds. I will go to that thing. So we have got, one is electrostatic accelerator, another one is RF accelerator. So these are some of the components needed. Lighter is not there. Okay. So you will have a high voltage generator, and there is an accelerated column, and then how particle is accelerated and used for various applications. Okay. This is the first accelerator in India, 1950, in TAFR, Tata Institute of Fundamental Research. Our Homi Janani Baba, he has installed this one in 1950. And the further chronology is given in this booklet. I would like to give to the Institute library, Vishnu sir can take later. So these are different types of accelerators. Linear, we have made electrostatic and RF. Circular accelerator, cyclotron is at the VCC Kolkata. You have the opportunity, you will see that. And then cyclotron is in RFCAT. Based on the application, we have got industry, medical, environment, R&D. Based on the method of acceleration, we have various types superconducting, and particles, electron, proton, and heavy ion can be accelerated. Okay. So these are various accelerators available in India, in DAE as well as private. So about 450 numbers and more accelerators are there. So you call it anything, A to Z, electron accelerators or proton can be used for medical therapy, cancer diagnosis, or taking X-rays, we need electron beam. X-ray tube is having electrons. And then you have the tire, whatever automobile tire, they are all crafted by electron beam. All plastic parts are electron beam treated, and so many things. You will see that further application. And this is the wide spectrum of users, industry, medical, national security, for scanning the truck, containers, and baggages, everything. Electron beam and further X-rays produced by electron beams are useful. Okay. So these are the applications which we have demonstrated in Electron Beam Center, Karwar, Navi Mumbai. If you come to Mumbai, you will have a visit to BRC. And one invitation to all of the students, every year there is a DE essay contest program. You can participate in the essay contest, and you can visit, you will have an opportunity to visit BRC. And this is the kind of energy and the dose rate. Dose is the energy absorbed by the material, unit density material, and joules per kg. And if you give 1 ml, it will penetrate 4 mm of water. If you give 10 ml, it can penetrate 40 mm of water. Okay, that much it can penetrate. If it is converted to X-ray, it can still more penetrate, and it can make the bond and linking and so many activities. Okay. So these are some of the types of accelerators. This is one of the first accelerators inaugurated by the then Honorable Prime Minister Manmohan Singh. I request one video clip.
short video clip, you will see the full operation of the accelerator.
Bhabha Atomic Research Center, in collaboration with Samir Mumbai, has embarked on realizing the development of industrial electron accelerators at Electron Beam Center, Kharghar. 10 million electron volts radio frequency linear accelerator RF LINAC is currently operational to cater to various in-house and exploratory scientific and technological radiation processing requirements. This range of electron acceleration energy to 10 million electron volts is the limiting value for industrial applications. Beyond this energy, there is fear of radiation activation of the product undergoing electron beam processing. The technology has basic building blocks comprising of the source of electrons called electron gun and an accelerated structure made of oxygen-free copper cavities integrated by special brazing techniques. This structure, employed for acceleration of electrons in 10 million electron volts RF LINAC at EBC, is termed as standing wave structure in scientific parlance. The LINAC is powered by a microwave source commonly called as klystron, which powers the cavities to build the required RF fields in the structure, where electrons pick up desired energies and propagate in vacuum. The modulated pulses of the power source for the electron gun and the klystron RF source must be suitably synchronized so as to effectively couple energy to electrons. The accelerated electrons are then made to guide through drift region suitably steered by magnetic fields and finally made to scan while ejecting out into open atmosphere to process the desired product. At EBC Kharghar, 10 million electron volts electron accelerator has demonstrated effective processing of plastics, cables, neoprene O-rings, solar cells, electronic components and processing of PCBs, thereby making them recyclable. BHEL and ISRO are the leading names that have benefited by the processing of their products. The technology development of compact radiation sources.
I will cut short here. Later it can be played. And so this is the building electron beam center and how this is located and how they are safely operated. The moment you give the electric power, electron will be activated. If it is switched off, you can go and stay there, sleep there is no problem, no radiation. But when it is operated, the doors are closed, all the safety measures and radiation monitors are there. These are all provided as per the safety norms. Okay. So anything, if very simple tools, a knife can be used to cut the vegetables and it can be used to cut the throat also. Okay. Any scientific invention, science and technology can be used for useful purpose or destructive things. So always when we talk about the neutron or nuclear energy, we are talking about peaceful purpose, medicine and many other things. And next, this is various process of next, diamond stones, next. And this is some of the power devices, electronic devices, which are improved by electron beam. There are so many things. Further next. Solar cells which are going to satellite, 15 years they have to work, but before that it has to be qualified. So they can be qualified within few days in the accelerator. Whether they are suitable for 15 years, will be qualified in the accelerator. You cannot wait for 15 years. Next. These are waste recovery from the PCBs. Special materials can be extracted out. Next. And for the food preservation, electron beams and X-rays can be used. Next one. Next. These are some of the examples of food preservation. Next. This is one of the pesticides, pitosan, which is used for this sugarcane and papaya. It is regularly being irrigated in our plant. They bring the shrimp covers and they irrigate it and they put it in the sugarcane. They get 50% yield. It is not a magic. It is proven technique. Yes. And they have given the certificate. Pasandara sugar is the next one. This is about flue-gas treatment and wastewater treatment. How the process is happening, the OH radicals, they make the useful things. Similarly for the wastewater also, water can be treated into biodegradable. Otherwise, we are polluting the water bodies, and one typical example is Ganga, Yamuna, and all our rivers are polluted because all industry waters are thrown into the rivers and sea, and which can be prevented at a CETP, common effluent treatment plant, an electron beam, and many other methods. Next. These are carried out, Bhaskaran sir has witnessed in our electron beam center. Flue-gas treatment in coal-fired thermal plants, we can use this, but we need a large electron beam power plant. Accelerator. Next. Next one. So this is an example of pollution in Ganga. What are all the causes that are happening and what are the parameters we need? pH values, POD, COD, TPCB standards. But we are not following and it is exceeding. But how we can reduce, recycle and reuse by various methods. Next. So this is one of the methods which we have adopted in EBC Kargar. So here we can treat per day 2 million liters of water for about 10 kilogram dose can be given to them. Next one. These are some of the water which are treated at the different electron beam radiation and their COD, BOD are reduced. Next one. This is for security application. You can play the video now. Just, maybe it will be another 2-3 minutes. It will.
The Gantry Type Scanner. Gantry Type Scanner, ICSG-V1 and Gamma Field EARC is an indigenously developed prototype machine that can scan all vehicles or trailer-mounted containers within sizes 4.6 meters tall and 2.8 meters wide. Overall size of gantry is 10 meter wide by 6.5 meter tall and 3.6 meter deep. It holds a detector array with collimators on one side and a 4-ton secondary collimator and X-ray source on the other side. The gantry is driven by a servo motor through rack and pinion at a constant speed of 0.4 meters per second on 3 dual grades. The gantry is insulated and air-conditioned for the safety and longevity of the subsystems. The gantry structure has special provisions for safe loading of equipment. The alignment of collimators is done to establish exact matching of fan beam from primary collimator to the detectors, and the rigid design of structure keeps triangle ABC undeformed during gantry movements. Upper floors of multi-story gantry contain power supplies, chiller, modulator.
This electron beam converted into X-rays can be, without opening the container, you can see what are the things inside. Whether it is organic or high metals or any explosive or anything can be scanned, and before opening they can find out. So this has been made in DRI and we are going to install in Jawaharlal Airport Trust in Navi Mumbai. So next, I'll come back to the final thing. Accelerators for power generation. And our topic of nuclear energy for sustainable tomorrow. So how nuclear energy, the waste disposal, and there are so many issues in handling the nuclear energy. Nuclear energy is very clean and very less carbon footprint, but the actinides, some of the actinides, plutonium and anti-americium, and these are all having very long years of decay. So how it can be handled? So this is by this technique called accelerator-driven nuclear reactor. It will be operating at a subcritical level. Whenever you want, you switch on. Whenever you don't want, switch off. Otherwise, nuclear reactor, once it is started, you have to keep on running. You cannot stop. You have to put the poison rods only to stop or dismantle everything. But here, you can use the photon energy, and if it is at the last we are having. This is a picture. There is a linear accelerator, and there is a target, lead target or uranium target, and one proton can produce 20 neutrons in a lead target. So whenever you want, you can control the electron beam, current, and number of neutrons you can control. So this is always operating at a less critical value, and presently the first stage, 20 MeV has been made in DRC. This is the pride of our country, India. We have made 20 MeV first phase. We are planning to develop 200 MeV and 400, 800 MeV in Vizag in the next another 10 years time. So this is the first stone. That's all. So we welcome all of you to BRC and Electron Beam Center to learn more about these accelerators. So it can be used for common, normal, everyday use, or it can be used for the nuclear power generation also. It can be used for material studies and electron beam or these accelerators, high energy accelerators can be used for colliders and the birth of universe and the future prediction of what is going to happen. So you might have heard about Big Bang machine, and there I have worked 1 year in CERN Geneva. So you are invited to go through this in various Google or in DRC website and various forms. You can learn more about the accelerator. Definitely it is useful for us. So that's why I have given the conclusion. Development of indigenous accelerators makes us Atmanirbhar Bharat, and transfer of technology, various technology has been transferred, and so that by 2047 we can be Viksit Bharat. Thank you. I'm sorry for more time taken.
Actually, from Dr. Bhasin, we can learn so many things, but unfortunately, because of the time restriction, we have to cut short. And during the tea break or lunch break, children can interact. Thank you.
Is there a plan to give, make air accelerator to be made to given to universities in India where research can be carried out? Is there a plan or is there a way of doing it?
Yes, through ECL, Electronic Corporation of India Limited, we can give the technology. We have already transferred the technology to private firms. Small accelerators can be made.
Sir, good morning, sir. I am an MSc student.
Thank you, sir. We had such an engaging session. Now it's time to express our gratitude. I would like to invite Dr. K.V. Das to present the memento and the book on the Wheels of Education Serving USA in India, written by Professor Sree Krishna, a renowned scientist, to Sri R.I. Bhatt Singh.
Yeah, it is the next time to introduce our resource person of the third session. Sree K.N.S. Nair is going to deliver a talk on experiences of setting up medical cyclotron facilities in Kerala. A brief introduction to the resource person here. Sree K.N.S. Nair is a mechanical engineer who graduated from the Regional Engineering College, presently NIT Calicut, Kerala, and did his post-graduation from the Indian Institute of Science, IISc, Bangalore. He has over 35 years of experience in nuclear projects, essentially related to nuclear recycle program, and was ex-chief design engineer and head technology development division in Baba Atomic Research Center, Mumbai, India. He is an expert in the design of radiochemical facilities, fuel waste processing, radioactive material transportation, and design of processing laboratory hot cells. He currently manages the hospital and cyclotron project of Molecular Group of Companies as a director, facilities management. On behalf of you and the Department of Physics, Sree Krishna Guruvayur, I invite you, sir, for the talk. Thank you.
Sree K.N.S. Nair.
Work ചെയ്യുന്നുണ്ടോ? എങ്ങനെയാണ് ഇത് ഫോർവേഡ്? So, good morning to all of you. Thank you for giving me this chance to present an experience, actually. There is not much theory in my talk. This is an experience, what we have done in Kerala. I have been introduced yesterday as a waste management person, but this talk will not have anything connected with that. My colleague Anand Ganathan will give a next talk, that will be purely on waste management and radioactive waste management. So I am presently working with Molecular Cyclotrons Private Limited, where we have installed a medical cycle. Doesn't work? Huh? So my plan is to talk a few sentences on medical cyclotron. I am a mechanical engineer. What I have heard and learned from my colleagues, that's what I have. Cyclotron facility in Ernakulam I project, how we will implement it. Some societal impact, it's how it affected like cancer treatment program in Kerala. Our experience and future plans, molecular group, I will introduce the group. Next one. To completely talk, actually, this basic principle has to be presented. You have heard from Dr. Singh, a lot about the linear accelerator. Now, the cyclotron is a circular accelerator, a compact thing, medical cyclotron, and here, fluctuating voltage, alternating current, voltages are applied in a sequence and in a magnetic field. So, a charged particle can get accelerated in a spiral form and it comes out and hits a target. And if you keep a material, target material of your interest, you can make some radioactive isotope. That's what it does. What we have done is we have imported the cyclotron from Siemens, Germany, and installed the associated parts designed the lab and got it done, approved by Atomic Energy Regulatory Board. So, we talk about the medical cyclotron. They have to produce radioisotopes for pharmaceutical use. Major isotopes produced are fluorine-18, nitrogen, carbon-11, oxygen, 15, gallium, thallium, and copper. There are many others, but these are the general isotopes which are made. Isotope with short half-lives and low medium energy is preferred for medical applications. In the first talk in the morning, there was very clearly explained how the medicine has to pass through your body and come out. So if you use a half-life material, it will stay in the body. Wherever it stays, it can be there for a long time. If it is so, this energy, whatever energy is required for your intended purpose, that is either imaging or therapy. That is what you should aim at. Cyclotron should be ideally located in the easy reach of the hospitals. So you have to strategically place it actually. Then label compounds are used for diagnostic imaging of cancer, heart ailments, brain, like Parkinson's or such things are also disinvolved. Molecular cyclotrons, Kochi. So the company, we installed the first and only medical cyclotron in Kerala. This is the only medical cyclotron in Kerala. Established in Valpur Island, 5 kilometers from Ernakulam, produces radioactive fluorine, F18, based medicines for diagnostic imaging of cancer, Parkinson's, and bone scans. F18 has a half-life of 110 minutes. From Kochi, we serve to Kozhikode, Coimbatore in the north, and Thiruvananthapuram and Nagarjunasagar in the south. We produce the medicines in the night. Maybe by 1 o'clock we start producing, and by 7 it should reach all the hospital. So we have 3 or 4 productions, which ensures that, comparing the distances, we make it reach them by at least 7:30 in the morning, because the patients are waiting with empty stomach for last 10 hours, previous 10 hours, and most of them, many of them are diabetic. They cannot have empty stomach for a very long time. As in the morning network, we have got about 28 cyclotron centers in India. This is distributed in about 12 states only. So there are many areas in India which are not even covered. Kerala is lucky to have one, because we, after retirement, 2 of us, came from VRC, and we could fortunately find some investors who are interested or who can spend their money on a subject which they don't know. They don't know much. There was only one medical doctor. He was actually a nuclear medicine doctor, but he didn't have much money. That was the difficulty. So there are some, so you can see the spectrum actually. The middle of India, many of these areas are not covered at all. Even Tamil Nadu, only one center. So when we started, there was only one CT scan center in Kerala. That was in Amrita Hospital. Now there are some 22 scanning centers, just because we came. So this cyclotron has to proceed, it has to come first. Generally, they can have the medicines. It has to be near the hospital. So now Ernakulam has 7 centers. And I think in Kerala, they have to travel only not more than 50 kilometers to get to a person. Because in cancer treatment, not only the patient, a bystander or number of bystanders, as a standard goes in Kerala, they travel along with them. So the cost involved, the psychological impact involved, everything matters. So I consider myself to be really happy to have got into this project and have been associated with it for the last 10 years or so. So we make FDG, fluorodeoxyglucose, we make FDOPA, in neurology, psychiatry and oncology imaging. We make F-colin, prostate cancer, FPSMA, prostate cancer, sodium fluoride, bone scan. The FDG are most common medicine for this CT imaging. Each cancer is different. Okay? But there are some common features. Cancer cells are dividing fast and hence they need pure glucose. So we make the fluorine, as Dr. Ray said today morning, we synthesize this into glucose. And glucose are required for growth of our cells, and cancer cells require more of them. Okay, so they go to the fast dividing cells fast, and so that scan, that FDG has become like an X-ray for normal ailment. So cyclotron facility, if I typical layout, it will have a bunker. A bunker is a vault, or a bunker is a shielded facility in which the cyclotron will be there. Cyclotron can be self-shielded or unshielded, depending on the energy it has got. We have, in Kochi, we have a self-shielded cyclotron. So, typically, you have a bunker, you have the hot cells. Hot cells are where this is synthesized, then the quality control lab, control room, and everything. So, you have to have a large area of controlled environment, that is temperature, humidity, everything should be controlled and kept. It is very important for the machine as well as for the product. As you have told here in the morning, for pharmaceutical products, both the person has to be controlled as well as the product has to be saved. Both have to be safe. So this is the cyclotron we have. This cyclotron is available. It's shown here to you, or any of you, or with your professors, some of you can come and see also. Of course, it has to be a good time. We have to take our prior appointment. So this is a reloadable cyclotron. There are a small cyclotron for medical purposes. 2 into 60 micrograms. So you can see 4 targets are there. For this weight was about, weight of this is a self-shielded cyclotron. The weight is about 48 tons. So 48 tons came in 7 parts, and we had to install that, in that area. Kerala had we had some problems in this. And the first and only medical cyclotron. Bunker wall thickness is about 600 millimeters of RCC. Bunker height 3 meters, roof height. We had a plan for introducing the cyclotron from the rooftop, so we had to keep on opening. That front had about 17 tons. That was the heaviest item. This is the cyclotron. This weighs about 5 tons. Here a small cyclotron, maybe of this table size. That's all. What you saw outside is the shielding. So in this cyclotron, they say even when the cyclotron is working, you can go inside, but that's not possible. You can switch it off and go. Because most of the neutrons, after they have died down, you can enter that room. This is the control room. Hot cells. Hot cells also are very important. These are shielded rooms we create with a negative pressure inside and a clean room. The clean rooms are, shielding is about 75 mm lead and 100 mm lead. Class B means the particles or the biological components what can be there, it has to be below some limits. Then the dispensing is done in a class A room. So, here from Mongolia and Netherlands, For our second project, we are thinking of making it in India also. These are the chemistry modules which converts the fluid 19 made in the cyclotron, transferred to the hot cells. They have been converted to chemically processed to produce the FDG. We have 3 synthesizers. This one, the last picture we show is the dispenser. So each hospital tells us in the night, evening, how much they require. Okay, so each patient may require about 10 millicurie of the FDG, the fluorine. So what we say, we have 10 patients, so give us 100 millicurie or 200 millicurie, whatever. So we have to send it to them in the morning. Okay, they can reach in the morning. So this is dispensed very accurately in this automatic dispenser. This is how you have to check the transport containers so carefully that, they are outside surface dose is within limits. And they are dispatched with a document so that the driver on the road doesn't have any problem. In this case, the quality control is done when the FDG is being taken to the hospital. So our largest distance is about 200 kilometers. So the basic quality checks, they can be done within 15 minutes to know whether biologically the effect is there or not. Any toxins are there in the endotoxin test can be done in not very small duration actually. Our other tests will follow, but by the time they reach the hospital, we will exactly know that the medicine is good for the patient. So we can call back the medicines. But in the last 7 years, we have not had even one incident that we had to call back the medicine. This comes from the procedures you keep in the laboratory. See, the GMP procedure, good manufacturing practices are followed. So everything goes through HL actually, before it goes into the production. The QCM has some gas chromatograph, some TLC scanners, and the endotoxin test is being done. The whole facility is flooded with a lot of radiation detectors. It is continuously monitored 24/7. So where if higher radiation levels are there, we will come to know. Fortunately for us, we have had no incidents so far in the last 7 years of operation. This is being followed up by the ERB also. They have to have a record of all these things. So, where we face problems, when you start installing, you have to have many approvals, okay? So the basic thing is coming from the regulator, Atomic Energy Regulatory Board. Local center volume, so Panchayat has to give so many permissions for the land and everything. The building design layout, chief town planner, government, environmental release, pollution control board, fire safety, rescue, Kerala government, and most of the things, we know that. The ARB approval is the most important in this case for us, for the safety of the operating person, as well as for the general public. So, site layout orders we have to have staging in stages of approval. So if you have a land or a location, you have to get an approval. Then we have to get a VSR and a design and construction approval. Pre-commissioning trials, final safety analysis report and approval of transport packages also. So the license will come, license to operate will come only after this is done. We have gone through this, it has taken us almost 4 years to get all the approvals done. Another difficulty was during the construction time, this has to be installed actually, in this particular case. It was a difficult operation because we had to have a top level thing, so 100-ton crane, whatever crane was used. So many underground pipes, about 1 meter below it goes, all the pipes are out. at the beginning of the installation. That means we have a 5 gram on thick slab below, then we have 1 meter below where these are being run. So the transfer of the radioisotope solution from the cyclotron to the hot cell. They take place through these pipes actually. Not these pipes, but the capillaries in these pipes. They are introduced through this. So at the time of installation, then lowering the shields, lowering the pipe. So running this facility, you need so much of support devices, support services. You need power, this power, 250 kW power has to be available. UPS has a 30 minutes rating. You have to have compressed air, high purity gases, chilled water supply, HVAC, this has to be centrally air conditioned. And the temperatures and the humidity are controlled within 1 degree Celsius and maybe 2-3%. So, once two exhaust systems are there for safety, they are exhausted through filters. They are monitored also. The exhaust is monitored. 24/7 radiation monitoring and data safety, fire alarm and mitigation system. It is a typical HVAC thing which comes to the control room, where you can see all the parameters, what is the airflow, what is the temperature at different locations, what is the humidity, all things, and any of them will give alarms actually. So we can immediately attend to this and correct it. So many compressors and the filters are in those boxes, that is the HU for the box. I would like to talk through some of the Kerala experience. Our approvals took a lot of time, local approvals. Area approval was the most straightforward, I would say. If you are right, they will give approval. If they have some questions, we should answer. But all other things, it's not so straightforward. The questions are asked many times, not because there is a problem. Okay. So you have the problems is in market, where you have shortage of even if you have to get a very good screw, a quality screw or a wrench, this is not available in the Bangalore market. You have to go to Coimbatore or Bangalore to get it. Production capacity, I will not about external interference because that is there. Political interference is there. That delays our product. See, ideally a product like this, 11 years cyclotron should take not more than 2 years. We have taken almost 4 years or 4.5 years. Capacity wise, we are not saturated. When we started, as I told you, we are only one customer, potential customer whom we are not sure they will buy from us. Now, there are some 22 centers. So, and we are almost, we have run 3 ships to get it done. Probably with hospital in the building, in our design, we have the cyclotron placed in a hospital building at the ground floor. So that also is not a good idea. Even if it is associated with a hospital, you should have a separate place. Radiation medicine center should be, the cyclotron center should be separate. Radiation medicine center can be there, cyclotron center should be a separate building, then it gives better control over the construction and installation operation. Because, radiation release problems will not be there associated with. Okay. See, how we did, from my side, being a mechanical engineer, many of the important items are very expensive. So we made a local dispenser. And because, we had a dispenser imported from UK, and that was costing about 22 lakhs. Okay. When we wanted to have a problem attended to him, he is asking me to send that back to them, and that will cost me almost 25 lakhs. So what we did now, we employed a company in Kochi. So we interacted with them. This dispenser is very good, and it can also have the accuracy of dispensing or all those features, except for the good. They are not able to give those good looks. The product finish they are not able to give. Otherwise, it's doing the job. We did it in 8 lakhs. Similarly, the transport container. We developed the transport container. We got it approved through ARV. The cost of the transport container, what I showed you, was about 3.5 lakhs each. And we require about 25 of them. It's a very big cost. So when you wanted a replacement, that cost is not very good for the profit conditions of the company. So we started thinking of making it in India, and now this has got approved. Now we have our approval, and the cost was about, actual cost is about 25,000 rupees. See, without including, my cost or, like overheads or something like that, which also can be added if you wanted to sell. So the products, most of them, some of them are readily available, some of them we have got it made. 25,000 and 2,50,000, you can imagine. So, typical. So, it is iodine 131 capsule, and dispensing is, iodine therapy is for the, hydrotherapy is for the thyroid cancer. And we have already started a facility where these medicines are distributed. We have initiated that. And the hot cells that was made in India, I would like to tell this, because the hot cell was costing, when you wanted to import it, before COVID it was costing about 7 crores. Imported landing cost in India. After COVID, they said because of COVID there is an increase of some 30 to 40%. So, cost will have gone to some 10 or 11 crores. The project was supposed to be closed. Actually, they didn't want to continue. Investors didn't want to continue with the project. Then we said we can do it. We get it made in India, and that was done in 3.5 crores, including the dispenser. So, we can do it. Atmanirbhar Bharat is possible. Please note kids, Dr. Roy mentioned in the morning. Please note kids, we are making now at least 7 kits, which is for use for the technician leveling, and they are being distributed to or marketed to various hospitals in our polygraphy. So the hospital is about to start. We have problems in getting the building approval for the hospital. That's a thing pending. So our inspiration is Dr. Amara Pillai. He was supposed to come here. He is a chemist, behind this show. He was heading the radiopharmaceutical division in GRC. We retired on the same day, and we joined this company on the same day. So our investors, they didn't know, except Habib Joy, nobody knew anything about nuclear medicine or anything like that. Very happy investing, Now we are thinking of a new project in Palakkad. We require MSc graduates, chemistry, medical physics MSc people, or people, or Dr. Roy has said, no. Not in large numbers, but good candidates. That's the last thing I would like to tell students here. See, physics and chemistry, when you learn biology, science, when you learn, opportunities you look forward. They are limited, but there are now. Please study well. Study the subject. Like BRC, there are many opportunities. To get into BRC, the interviews are very simple. But they ask you only the straight questions in the subject. It's not manipulated, So, that I have requested the organizers in the afternoon or so, they should tell you how you can get into BRC or IGCAR or, RCAT or something like that. Or to our discipline. Yeah. This is already, thanks already. They have got 14 staff, all of them are not in this, but about 25 are either MSc or PhD people are in PhD or MSc, and then engineers. Others are our drivers actually. Means they take the medicine equally important. Safely they make it reach the hospital. Thank you.
Hello. If anybody want to collaborate with them, you are welcome. And any questions, you can interact with him later on during the breaks. Thank you.
Thank you, sir. Now it's time to express our gratitude. So I would like to invite Dr. K.V. Das to present a memento and a book titled On the Weeds of Education, Serving USA and India, written by Professor Sree Krishna, an renowned scientist, to Sree Krishna. Sir, please. Now, to honor Dr. K.V. Das, chair of this session, and Dr. Santosh P.P., co-chair of this session, let me invite Dr. Praveen Kumar, joint convener, Nest 25. I hope you all enjoyed the session. Now it's time for a short tea break. Please refresh yourselves and back here in 10 minutes. Students who have registered for presentation for the afternoon session should report at the registration desk right now. Welcome back everyone. Hope you enjoyed the tea break. We are now moving to the session 5, which will focus on heavy water technology, waste management and rare earths. First speaker of the session, Sree M. Bhaskaran, Senior Scientist, former Executive HWB, retired. On the topic, Separation of Isotopes, Overview of Heavy Water Production in India, followed by Sri Anand Gangadharan, Head Waste Management Division, BARC, on Managing Nuclear Waste, followed by Sri R.V. Vishwanath, Chief General Manager and Head Rare Earth Division, IREL Kochi, on the topic, The Fascinating World of Rare Earths. The session is chaired by Dr. Susan Eapen, Senior Scientist, BARC, retired, Adjunct Professor, Bioscience Group, Union Christian College, Alua. And the session is co-chaired by Dr. Padmanabhan, Assistant Professor, Department of Physics, Sree Krishna College.
So, I have the greatest pleasure in introducing Dr. Susan Eapen, who is the chairperson of this session. She was a scientist in the Baba Atomic Research Center in the field of plant biology and botany, and retired in the year 2011 as a senior scientist. Since then, she has been continuing her scientific research and also teaching at the Union Christian College, Alva, as an adjunct professor in the biosciences group. She has had an illustrious and very active career in her respective field. And she is also considered as one of the pioneers in transgenic plant research, and her interests are varied from plant biotechnology, among other things. And to her credit, she has around 140 research papers and several books. And she has been bestowed with various honors at the national and at the international level. And scientists from many other countries have often come to her lab to get trained in the various techniques. She is one of the 75 women in STEAM, that is science, technology, engineering, arts and mathematics. And also she is listed among the top 2% ranking scientists as per the list annually produced by Stanford University, and she has been maintaining this since 2020 onwards. So, let us move on to the first talk. The first talk is by Sree Bhaskaran Mundayur, who was former chief executive in the Heavy Water Board. A brief about his academic background. He has a bachelor's in chemical engineering from the Government Engineering College, Thrissur, and afterwards joined the Heavy Water Board in BARC in 1980. He retired from his service in 2016, but still has been very active as a Raja Ramanna Fellow for the past 3 years. He presently resides in Angamali, so I would like to invite him for the first talk, that is separation of isotopes and an overview of heavy water production in India.
Good afternoon. Can you hear me? Yes. We have come to the second session of our today's program of Nest 25, and we have 3 distinguished speakers. Since we are running late, they will have 30 minutes of presentation, When it is 25 minutes, I will just remind you, please wind up in 30 minutes, and then one or two questions also will be followed after that.
Okay.
On the behalf of my co-chair and chair, I welcome you all to this session. Thank you.
Namaste. Yeah, I am talking a little differently on a different topic. Because we have been talking about reactors, we have been talking about the materials for the radiopharmaceuticals, isotopes and all. So let me just say that I am from Heavy Water Board, and we have been producing isotopes of interest to DE and other aspects. So isotopes we all know, but there are two types of isotopes, stable and unstable. So for example, I am going to talk about deuterium. Deuterium, boron, nitrogen-15, they are all stable isotopes, whereas tritium, fluorine-18, they are all unstable isotopes. So I am going to talk about the stable isotopes, which is of large use in atomic energy, which is deuterium. Once you consider the isotopes are very similar with physical properties and then chemical properties. There's hardly much of a difference. And then we tend to believe that they are similar, identical and all. But when you really want to separate the isotopes, which is of interest, we need to look at the different properties. So for example, heavy water, which is oxide of deuterium, and the natural water. If you consider the boiling point, see the second line, which is 101.4 for heavy water and 100 for normal water. It is of a very, very small difference. So when we try to separate out what are the different properties and what is the extent of property difference, that is what it is the driving force for the separation. But then you see that it's a very, very small, and when you consider the density or freezing point, they are all very similar, but a bit different. So, unlike the BRC and other units, we are an industrial unit under the Department of Atomic Energy, and our job is take the process, build the process, design and engineer the plant and set up and operate. What are the isotopes of interest to DAE and for the public at large. And so we are an industrial unit under DAE and set up very large chemical plants. And we have been in picture for the last 4 decades. This is a bird's eye view of Heavy Water Board where we stand in Heavy Water Board, that is an industrial organization. You have an R&D centers, public sector undertaking like NPCIL or IRAL. We are under departmental organization, industrial organization. We have service organizations and then aided institutes. So most of the people are aware of DRC, IGCA or TIFR, things like that. But the industrial units, people are not very much aware. We also come through the department setup and then join the industrial units. So here deuterium is a stable isotope of hydrogen, and they are all oxygen-18, boron-10. So we produce some of the oxygen-18 separations, so we work on that. Boron-10 also we work on that, which is of interest. But the largest interest for running the reactors are deuterium, which is moderator and coolant for the system. The issue is that we need very large quantities of heavy water, and the presence of heavy water is very small, which is 144 ppm in the normal water. And we want to concentrate to 99.84. So we need to have appropriate separation technologies, and which is not costly. It should be economically viable processes. So if you think of separation, so for example, when you are having water and oil, the density difference is very large, so it is easy to separate. So you can, based on density or centrifugal separators, you can separate. If you want to distill, like water and alcohol, which is having a large boiling point difference, so it is much easier. If you want to remove particle size based salt and sand, you can dissolve in salt and then remove the sand. Same way, absorption, carbon dioxide and air, or adsorption with membrane, nitrogen and air. The process all depends on physical and chemical property difference, and quite large difference. Whereas in heavy water or deuterium, the property difference is small, as we have seen, and the enrichment required, or the terminology what we say is the enrichment, the multiplication of the concentration, is almost 10,000 times. Which if you really look at the alcohol water separation, what you need is only 1 or 2 maximum, which is 10,000 times in case of deuterium. And various processes are there, and Heavy Water Board has been working on various processes, and then we have made the plant and then produced heavy water in a large quantities, and we are the largest producer of heavy water in the world at then, and we are exporting substantial quantities to the developed world also. So we have some distillation process, but distillation, since the times of enrichment requirement required is around 10,000 times, so you need to process that much water and then distill. So it's not economically viable if you are starting from 144 ppm. So what we generally do is certain chemical properties, the chemical potentials are slightly different for H2S, H2O system. So there are few systems which we have developed, and then this is enriched deuterium is transferred from one phase at one particular condition to the other phase at a different condition, what we call as separation factor, depending on the chemical potential difference at different pressure and temperature. So there are 4 systems which works for this exchange process, which is one is H2S H2O system, the other one is ammonia hydrogen system, ammonia water system, and hydrogen water system. So the last 2 ones, hydrogen water system, we are ready with the system. In case it is required, we will do it. Ammonia water system also we are ready. In case if it is required, we can set up the new plants. Hence, the Water Board has prepared complete process, technology, design, and everything is ready. Whereas we are present, the existing plants are operating on hydrogen sulfide water and ammonia hydrogen water. So world over, hydrogen sulfide water was the process which is used. But India, because of various uncertainties, we have gone for both the process, and then we have gone with the ammonia hydrogen process also. So some of the plants are working on ammonia hydrogen, whereas the other plants are working on hydrogen sulfide. So this is how we have come to the various design engineering. In DE, we are one of the major organizations who is designed to concept to commission. And we are the leading producer of heavy water and fulfilling fully domestic. Even I joined the department. We were looking for heavy water, and then we were thinking that there is nobody to give it to us, and then that was one of the main problems and the delays for the PSWs. But then today we are surplus. We are waiting for the power plant people to come and then take it. It's quite a bit of surplus at the moment. So the complexity is because of low natural abundance, low separation factor, very high enrichment scale required, and because of very high enrichment is required, the type of contacting divisions, if it is a gas and liquid separation, what we do is we contact gas with liquid, separate to one phase. Then another temperature pressure condition, we have another contacting, and then the deuterium is transferred. And this deuterium transfer between gas and liquid, we cascade the volumes. For example, when we start with 100 tons, the first case, the second case we will be reducing that particular thing to 20 tons. Third phase we will go to 2 tons, and then fourth phase we will come to half a ton. So that is how the concentration profile is built up. And so we need very specific contacting devices. Unlike the other chemical plants, we have very separate high efficiency contacting devices. And this requires, or this mandates, specific material for construction. For example, we have a ammonia cracker, which we require, it's a high pressure, high temperature ammonia cracker, for which we require Inconel 625. We have been using Inconel 625, which other people are using presently, for the last almost 55 years. And then obviously ammonia, hydrogen sulfide, hydrogen, phosphorus alpha. So we go through all these parameters for selecting the process. We started in 1954, considered the first plants when Ramana was there, and or prior to that thing when Arabai was there. He was the first one to promote heavy water board and then form heavy water board. He was the first chairman of heavy water board. And then we started building systematically the heavy water plants, and then today we have 7 heavy water plants. 4 of them operating. So this I will leave it. 48 to 54 to 56 is the first heavy water production at Nangal unit, which was electrolysis for hydrogen production by fertilizer plant, because the power was very cheap at Akra Dam for electricity production. And we have a cryogenic hydrogen liquefaction and distillation. The plant is not operational because it is no more economically viable. So first production was in 62, August 9, started in 56. This was a fully imported plant from India. Then we formed heavy water board on May 1st, 1959, and then the story. So we go through the various steps for technology development, and takeoff was at Nangal plant, and then marching ahead with the other monothermal and bithermal. Today we are having plants at Baroda. The plant is no more operational because we have already consumed the entire life. The Tuticorin plant, which is presently shut down, which is under revamping and then restart. Alchar plant we have stopped heavy water production. Kota is operating because we have been operating it right from beginning. Second phase are Manuguru, Thal and Hazira. This is the second generation plant. And the third generation plant we are ready in case SWR or the SMR programs require. Because whatever 17 gigawatt SWR program was envisaged earlier, the entire heavy water is available to operate it to the end of life. But then in case new reactors are coming, which is the thinking at the present, then we may have to set up this plant. So that is what I said, planning for further capacity addition. So these are the different heavy water board plants, heavy water plants, which is across the country. Kota is working. Baroda is not working with heavy water production, but we have a lot of solvent production. Also we have solvent production and then boron production. Thal, Hazira, Manuguru, Tuticorin, we are operating heavy water. So this is what we have already discussed. If you really look at the nuclear properties, the normal water definitely is having a higher slowing down power. Slowing down power means you are having 1 unit energy. After a collision, how much the energy comes down. So it is something of that order for the slowing down power. To look at the heavy water, water is having a very high slowing down power compared to heavy water, but it absorbs neutrons. So that is why normal water is not used as a moderator. Whereas if you look at the neutron capture cross-section, is much higher, lower in heavy water, so that the neutron loss is limited, so that moderating ratio is very high. That is why heavy water is used as a moderator. And what required is 1 megawatt of PSWR, it requires around 3/4 ton of deuterium, heavy water. So these are the different separation. Electrolysis is very possible, but highly energy higher energy requirement. Distillation, for the higher concentration, it is possible to upgrade. And distillation of hydrogen, if hydrogen is available, we can liquefy and then distill, but hydrogen is not available or was not available so far, but now with hydrogen production going to be higher, probably we will be able to revisit these things. Our plants are operating with H2O operation, ammonia hydrogen operation. Because of ammonia hydrogen we have to be linked with the fertilizer plant. And then water hydrogen exchange process, which is not yet ready, but catalyst is ready and every other aspects are ready. So this is the chemical exchange taking place in H2S water. We have deuterium driven to the liquid phase at 30 degrees and driven back to H2S at 130 degrees centigrade. Whereas in ammonia hydrogen, there is a monothermal process. We operate it at -25 and then higher pressure of 200 bar. So the deuterium is removed from the hydrogen gas to the ammonia phase and then we concentrate the thing. So ammonia water, we had a plant at Baroda. We have operated for 7 years and then collected all the engineering data and then ready with the preliminary engineering. So this is a typical flow sheet for H2O process. Cold and hot hours will be there. So the deuterium goes up and down and then the mass cascade is built on that process. And then finally we distill water and then get the water. This is the almost the same way ammonia hydrogen exchange process. But the thing is that it is connected to a fertilizer plant so that fertilizer hydrogen is passed through the water. All hazards are there. Whatever you are handling, hydrogen, ammonia, H2S, because H2S is very toxic. We handle very large quantities of H2S, but we have been fortunate and then we have done the safety engineering so well that accidents are not happening. So many other requirements, potassium metal and all these things we produce in-house. So these are the design production capacity and then the status of the water plants at the moment. Look at the water quality what we are having. The isotopic purity has to be 99.85 for reactor. We have a special product which is more than 99.90 up to 99.9496. pH, conductivity, see this is, conductivity is very critical, less than this, and the chloride content. And the other one, fission activity, probably lowest fission activity in the world, what we are having is Indian heavy water. So I will just have a look, please have a look at the different, this is an annual plant. Backside you are seeing the cold box. Now the plant is no more dismantled. This is the plant at Kota. We are having various columns, what we are seeing. They are all different cascades and then the first cascade, second cascade, third cascade. And this is with 100 ton heavy water production. The steam is coming from RFS. This is the largest heavy water plant in the Asia region and in India of course. This is at Manuguru in Andhra Pradesh, in Telangana. This is around 200 tons production. Same thing, it is a repeat, 2 stream plants are there compared to Kota, another stream is added here. But with lot of energy, because what we require is lot of energy, and for energy production we are having a captive power plant, coal-based captive power plant with 90 megawatt electrical what we can use. and we are having a 12 megawatt peak solar plant supporting it. So this is a huge system, and then we produce almost 1500 meter cube of our PM water quality plant. Probably it is higher quality than whatever is required for a steam generation. This is the Baroda plant. It is still existing, but then we are not producing rainwater. This is Tuticorin plant. There was some problem with the split plant with which it was connected because there was some naphtha operation earlier. Now the gas has come for ammonia fertilizer production. So we are again going to restart this plant. Restarting, refurbishing of the plant is going on. This is the plant which we commissioned in 1986. This is connected to RCF hall at Maharashtra, and this is 100-ton production. It is near to Bombay, 100 kilometers south of Bombay. And this is the Hazira plant, Litho plant, but it is connected to Tripo plant at Hazira. This is Talcher plant. We had a bithermal water plant, and bithermal operation, ammonia, deuterium going to ammonia to hydrogen and back, that type of cascade. But the plant did not operate because of the fertilizer corporation. They stopped their fertilizer plant. And then we modified this thing for the other required materials, which is basically solvent and boron. We'll come back. So these are all challenges. They are all very corrosive things, toxic gases. So what is required is effluent management, energy. There is a, to look at it, the energy whatever in 1998-99, we were having almost 44 gigacalories, gigajoules per kg of water production. Because if you look at it, why water is costly, it is the energy input cost. And if you really look at it, what is the water production cost in Western world? Where the energy is very cheap. And you look at Indian energy cost, it is manifold higher in India. So, but still, we are able to compete with the world, basically Canadians. And then we have been able to bring down from 44 gigajoules to 30.5 gigajoules in 20s. But then it is almost plateaued. It is, there is not scope for further reduction, unless there is a very large capacity capital. So this is what I have already, we are already geared up for 17 gigawatt production, whatever has been planned for that 10 gigawatt was planned by NTC. But if it is 4, which is under planning, we are going to set up. The other one what was happening is, we have been able to export heavy water to all the developed world. And this export of heavy water is for nuclear requirements. They have exported to Korea quite a good quantity for their reactors. But presently whatever export is there is because of the non-nuclear applications of duty and heavy water. And what has happened is, there is a deuterium, if you are substituting in the molecule, it is there for electronics, it is there for life sciences, it is there for other memory, electronic memory storage, and then all sort of things. And that scope is increasing. We have also been trying to do something like promoting the Indian industry for that. But then it has not come to that level. But quite a bit of, the system has come up in the country, and then producing deuterated APIs and then like that. For example, we have been supplying deuterium gas to sterilize optical fibers. Because what they do is that by treating annealing in deuterium condition, the free radicals are removed, OH is replaced with OD, so that the aging effect for the optical fiber is reduced. So quite a bit of, that's a big topic for the thing. We have been promoting it for the last 15, 20 years for the non-nuclear application.
Excuse me, can you wind up in 10 minutes?
Overall. to design and deployment. And then we do a lot of energy management because the energy required is extremely heavy for heavy water production. And of course on process safety and industrial safety. And resource management, these are all whatever we have specialized. And the other activities, having completed heavy water production, the other isotopes what we produce is boron 10 enrichment. We can enrich up to 99.94 and above boron 10. And then what we get is boron 11, which is with the equal enrichment, which we have been able to supply for the electronics world over. And the plant is there at Manuguru and Talcher. And we have some plant, we were operating a plant for removing important material, which is uranium, rare earth and things like that, from phosphoric acid. We have been operating that plant successfully because we produce solvents, we have solvent extraction technology also. So we have been able to operate this plant. Like my friend KNS9 said, they use oxygen 18. We are producing oxygen 18 in our Manuguru plant. We have conceptualized the design and then we have set up the plant ourselves. We have some units which is presently working for recovery of gallium, cobalt from secondary resources, some helium production, since we have groups, because there are certain purge gases which is concentrated with helium. And when various spin-off technologies, because when you do with the chemical engineering part of it, quite a bit of spin-off technology comes. We have an ammonia flue gas conditioning technology. We have various absorption refrigeration, not using electrical thing, but using very low quality heat, 72 degrees, 70 degrees temperature hot water. We are operating our entire chill water for 6,000 tons of refrigeration. And when we produce deuterium, you get deuterium depleted water, which is having again a very large application, which is a growing application. So we have been supplying that. And recently a water board has gone to set up a pilot plant for sulfur iodine cycle, using sulfur iodine cycle for hydrogen production. The plant is coming at RCF. Which will be the heat source will be put with the high temperature reactor and then up to that. So we are doing the chemical part, chemical engineering part of splitting water for this cycle. See, this is what I was telling. One of the spin-off technologies, you see these are stacks in Manuguru. The middle one, which is not having anything emission. The first one, it is not in service. The third one, there is a qualified power plant and then that is the emission. And the second one is with our ammonia conditioning technology, which is improving the efficiency of the ESP. That is how it has become fluoroscope or whatever sort of. We have patented it. We have a lot of power plants are using it in the country. Thank you.
Thank you, Dr. Bhaskar, for the excellent presentation. Now the presentation is open for discussion. There is time for one or two questions. If there are no questions, I would like to thank Sree Bhaskaran, who was the Chief Executive of Heavy Water Board, who has presented a very beautiful presentation on an overview of heavy water in India. Thank you so much. Please give him a big hand.
Thank you, sir. Now it's time to express our gratitude. I would like to invite Dr. Susan Eapen to present the memento and a book titled On the Wheels of Education, Serving USA and India, written by Professor Sree Krishna, a renowned scientist, to Sree M. Bhaskaran. Sir, please.
Thank you.
Now we move on to the next speaker. Who will be introducing?
So, the next speaker for today is Sri Anand Gangadharan, who is a scientist in bark. His academic background is, he is a chemical engineer. He graduated in 1999, after which he joined the BARC in the division of waste management, and currently he is the head of the waste management division in the BARC. And he has had 25 years of experience in the field of radioactive liquid waste management, covering a wide spectrum in the disposal and also the treatment of various types of wastes. And also he has considerable expertise in the development, demonstration and deployment of radionuclide selective ion exchange based plants. And his primary activities involve process design, project engineering, commissioning and operations of the waste management plants. So, and also he is a recipient of the prestigious DAE Young Scientist Award in 2006 and also the Group Achievement Awards in 2016 and 2019. The title of his talk is Managing the Nuclear Waste.
Next slide. Good afternoon, everyone. So I thank Sree Krishna College and for inviting me for this lecture. And in particular, I would thank Sri Govindan Rudy sir for giving me an opportunity. I see a lot of seniors of my research center here, and it is my privilege to present the report on waste management to them. Recently, I have heard in the Union Budget 2026, there's a lot of emphasis that we need to generate a lot of power by 2047, around 100 gigawatt, and nuclear energy will play a very important role to reduce the dependency on the fossil fuels and for development of our country as a whole. And you will find this on the Press Information Bureau website, Feb 3, 2025. And in achieving this nuclear power, often the nuclear waste is cited as a problem. So my talk will try to allay some of the fears associated with this. What do you mean by radioactive waste? So there are international definitions. We have definitions given by Atomic Energy Regulatory Board. So it's primarily a material for which there is no use foreseen as such, and its concentrations are more than hazard levels. So these things are, we are only addressing that kind of materials for radioactive waste. As you have heard in the previous speakers, you have a lot of reactors coming up, a lot of industries involving radioactivity, a lot of hospitals and other applications which are handling radio materials. So eventually some of them will give rise to some sort of radioactive waste which needs to be managed. Like any other industry, nuclear industry also generates radioactive waste. The only difference is, and against the conventional industry, radioactive waste production is hardly 1% of the total waste generated across all industries. And if you see, compare between chemical waste and nuclear waste, chemical waste, the hazard will not change with time, it remains constant unless its composition is changed. Whereas in a nuclear waste, by definition, the hazard potential goes on reducing with time. I just like to bring out how we are handling the waste. On the left side is the unfortunate thing that if you see any conventional waste, you will find piling up of all nuclear, normal industrial waste or municipal waste in the country. I won't want to name the site, but I am sure this is the case with all over the country. And in places you have about open burning, this kind of practices. And on the right side,
is how we are handling our low-level radioactive waste. It looks like an Olympic ground, something like a football ground. So this is the level of seriousness we give to radioactive waste management. I like to point out, if you are comparing the quantity, this must have come earlier, comparison between a 1 gigawatt nuclear power plant and 1 gigawatt thermal power plant. The last row indicates the quantity. So as I said earlier, the waste energy is very minuscule. A coal plant will generate almost 1 million ash, 1 million tons of ash per year, whereas for similar power plant, it generates less than 9 tons per year. How this waste is generated? So all of you are physics background, so you know the nuclear fission. So you have a neutron which will be bombarded on a uranium-235 fissile ready nuclei, and it will generate a good amount of electricity. Along with this electricity, you have got two proton nuclei which eventually end up as fission, what we call as fission products. So that ends up as a waste. Another scenario, the second row, uranium-238, it absorbs the neutron and subsequently gets converted over a period of time to one of the isotopes is called Am-240. We have similar such isotopes. So this also comes as nuclear waste. The general strategy in radioactive waste is very simple. It's not very complicated. You take the radioactive waste, say its volume is V1, activity is A1, and we reduce its volume. So that process we call as a treatment process. And by reducing its volume, we generate two streams. One a waste concentrate, in which the volume of the waste is very, very low, as against and a decontaminated waste stream, which will have almost equal to the original volume, but the reactivity will be very, very less. And the waste from the decontaminated waste is then monitored and released to environment. The waste concentrate is further subject to a process called as conditioning, basically stabilization. So if it's a liquid waste, we convert it to a solid waste. If it's a solid material, we package it in such a way that nothing can get leaked out. That process is called conditioning, and that conditioned product goes for disposal. And how do we monitor the performance? So we have for the treatment part of it, the second row, we have two parameters. One is called the decontamination factor, which is basically a ratio of the original activity to final activity. So that explains to what is the performance of the process. The second part is how much volume is getting reduced. That is the final volume, original volume and the final volume. So this for the treatment code, that was a performance parameter. For the conditioning, one of the major parameters is the leach rate. What is the leaching? How much amount of radioactivity is coming out of the radioactive waste packages. This is one of the important parameters among others. The basic tenets, so this is what I said earlier was a general strategy. That's how we will design a radioactive waste management process. Now there are basic principles in radioactive waste management that are followed in the plant design, operations, projects. The overall philosophy is to make the discharges or disposal as low as reasonably achievable. And for that there are four principles: delay and decay, dilute and disperse, concentrate and contain, and reduce, recycle and reuse. The first two things, the delay and decay and the dilute and disperse, are basically used for very short half-life radio materials in the order of say a few hours or days, so that it comes down to almost stable levels in a few days, and that can be managed as financially material. Our standard philosophy is to follow the third phase, the concentrate and contain. As the name suggests, you are trying to reduce the volume of the material and convert it into a very small form which can be easily handled. And the current emphasis on the last line, reduce and recycle, as I showed you earlier. And this entire philosophy is we want to establish as per the vision of our founder director. And just because I like to read this out, this is given in way back in 1960s, that is 65 years back. Radioactive materials and sources of radiation should be handled in atomic energy establishment in a manner which not only ensures that no harm can come to workers in the establishment or anyone else, but also in an exemplary manner so as to set a standard which other organizations in the country may be asked to emulate. So basically what we're trying to say is that what we do at the WMD, we want to set it as a benchmark so that others can follow similar practices. This is another set of principles. So once we have done with the basic principles, this is a very common, place hierarchy is a common term,
come across in conventional waste management, and it's applicable to waste management also. So starting is the waste prevention. That is, we are doing this by improving the continuous improvement in the processes. So you will simply avoid the generation of the waste. The second is the waste minimization, that is you try to reduce the volume which I explained earlier, treatment of process, in particular radioactive waste. Reuse. Wherever possible, try to reuse the material so that waste generation is reduced or postponed for a long period of time. Another is recycle, that is whatever material is generated, suppose you don't have a use of it, I convert it into another form and again reuse it again. And lastly, the disposal. The preferred approach is to from bottom to top so that the overall generation of waste or handling is lesser. And this applies to whole of waste management, whether it's research and development, whether it is doing design and engineering, or you're doing operations and maintenance. These things will apply to all the sectors. So what I'm showing you is a typical fuel cycle starting from mining and milling of uranium, converting it to a fuel, producing power in a nuclear reactor, taking it to a reprocessing plant to separate out uranium plutonium, and thereafter waste management part comes into play, wherein we have got the management of various kinds of waste and its disposal. And if you see in all these processes, all the plants generate what we call as low and intermediate level waste. Its characteristic is it is almost 97% by volume, so it consists the bulk of the waste with a minimal amount of activity. And high level waste, which is normally it will contain more than 99% of radioactivity associated with it, but its volume is quite low. And here I will focus on this one because of the activity part of it. And volume but typically very, very low. Another comparison, this is from a OECD annual document, comparison of waste from various fuel cycles. So across various generating processes, whatever I highlighted, spent fuel management, the relative volume is small to medium, its activity is quite high to very high, and relatively radiotoxicity is quite high. So this is the stream which is of concern to most of the people in the world, and with this which we will address. From there, this high level waste get generated. So you have a spent fuel on the bottom left. You can see the spent fuel bundle. It is cut. It is put into a vessel. Then you add nitric acid, boil it off so that all the solid form of material is now converted into a nitric acid solution. This nitric acid solution is then subject to what we call as a purex process. It's a very standard process. You will get to type KRTP2 or VTP or whatever. You will get the complete process of it. In the purex process, uranium and plutonium from the top are removed. That goes off further processing. And as far as I am concerned, only my job begins, and from the bottom, wherein I contain a solution, nitric acid solution containing fission products and actinides, which I further evaporate, and the concentrated part is what is called as HLW, high level waste, which I will address. If you see what are the important radionuclides in high level waste, spent fuel and reprocessing. After reprocessing, uranium plutonium is removed. The left hand side, the three orange circles, you have cesium, strontium, and uranium are all major radionuclides in the waste, followed by technetium. And then you have what are called the transuranics, that is isotopes with atomic number more than 92, and of which neptunium, americium, curium. Now why I have chosen these two? Because on the right hand side, if you see their half-life, cesium, strontium half-lives are around 13 years. Ruthenium quantity is high, but half-life is 1 year. And the others, technetium, neptunium, those with the skin color, are in few hundreds or thousands of years. So the aim of waste management is to contain and isolate these radionuclides so that it can decay down to innocuous levels over a very long period of time. So that is the primary aim. And how do we do that? So that we are doing using glass. We are utilizing it in glass matrix and for its long-term durability. What I am showing you the problem in waste management, high-level waste from reprocessing, I convert this into some sort of glass canisters, glass blocks. Where glass blocks are then, they have got post-production processes of canister welding, overpacking, transportation to a storage facility. Because all these high-level wastes are highly radioactive. It will generate heat during this radioactive decay. It's going to generate a lot of heat. And that heat has to get dissipated. So we have our special facilities where it is stored for a period of 30 years, 60 years. So that once it decays down, then disposal can be thought of. And finally, it has to be sent to a geological disposal facility. So India is one of the countries, 6 countries in the world to possess this technology of from generation of the vitrified waste product to its post-production processes, transportation and interim storage. You will have general question as to why you want to have a glass at all. So on the right side, if you see that the glass is basically a network of oxides. So we have a network, and in this network you have what those red circles are the fission-bound actinides, goes and traps in that actinides. So if you see glass, if you remember the 10th or 12th standard chemistry, all experiments involving acids, alkalis, organics, whatnot is done in glass. And so and it's done in glass and nothing happens to it. As long as you don't put the glass down, there is no same principle is being used. It's a highly chemically durable waste form. It is not subject to attack by water or most of the acids, alkalis, etc. It's got a good thermal and radiation stability. All these radioactive materials generate heat over a period of time, but glass is very good absorber of thermal energy also, and it is stable radiation also. And this process of glass making eventually reduces the volume. So I have a 500 liters of waste solution. When I actually vitrify it, convert it into a glass block, it becomes some 30 liters of vitrified waste product. So it has a very good polymer action. It's highly resistant to corrosion, and the glass manufacturing is nothing new. It's available. Your glass is here. They manufacture industrially. So the process of knowing manufacturing technology in principle is known very well. And the raw materials are very inexpensive. Silica, boric acids are all not very costly materials. And importantly, it's an international consensus. Vitrification of high-level waste in a glass, to go take up any literature anywhere, this is an international, it is a known matrix that is followed. Why do we choosing glass? What makes us to say that no, glass will stay for a very long period of time? The answer to that is we are looking at a natural analog. We are looking at whether similar things are available in nature or in nature. So I'm showing two things. One is obsidian glass, which is basically a volcanic of origin, and is a basaltic glass which is available in a Deccan Plateau, the Western Ghats. One of them is near Thane, 70 kilometers from DRC. This basaltic rock is almost 65 million years old. And if you see the composition, on the right hand side, basaltic glass, SiO2 is around 49% weight, and you have a few other chemical constituents. The basaltic glass closely resembles our high-level waste glass. So if this basaltic glass can be structurally and chemically stable for 65 million years, it is natural to say that high-level waste will also be similarly chemically durable for this much millions of years. So this is the basis on which we are trying to vitrify the waste process. Coming to the engineering part of it, how we carry out vitrification. So it's again nothing hi-fi about it. We have got high-level waste, contains lots of various what you call as corrosion products, fission products, actinides, chemicals added during reprocessing, and then you add additives, the glass-making chemicals, silica, boric acid, titanium dioxide, depending on the kind of high-level composition waste you have. It undergoes some 4 steps. The first is the evaporation, wherein the water from the waste is completely evaporated. Then, as I said earlier, this is a nitric acid-based solution. Eventually, you will have the high-level waste containing nitrate. So these nitrates are then in a step called calcination. When you increase the temperature, this nitrate gets converted to oxides. That's called as a calcination step. The third step is the formation of actual waste. That is, as I said, glass is a network of oxides. So in this step, network formation takes place. And last step is soaking. You want to allow that glass to be held at 1000 degrees so that it becomes homogeneous. And after homogeneous, it is drained into a canister. So these are basic steps of vitrification of high-level waste. These are the few melter technologies we have. On the first generation melter is what you call as an induction heated metallic melter. Induction is a very known process industrially. You can check out in available literature. It was adapted for radioactive waste management use. The first generation melter. It's a very robust kind of a system, robust material, so that different high-level waste materials can be vitrified. But it's got a limited capacity. Its capacity is limited to 15 to 20 liters per hour. On the middle picture is what you call as a joule-heated ceramic melter. It is based on resistive heating, I2R heating, joule heating. And it's got a higher capacity, so it can be used on a production level. But the issue is it's got a limited life, and it's very specific. You cannot change the waste as and when generated for this melter. And we have got experience at industrial scale with both the IHMM and the JHCM operation plants which are running both the melters. The third one is the advanced melter, which is what we call the cold crucible induction melter. It has the advantage of having a long life, and it also can handle variety of high-level waste. It's not that we only show pictures, schematics. These are the actual pictures, images taken from operating plants. On the left-hand side is the induction heated metallic melter. Since I don't have a pointer, I cannot say. The bottom half of the portion are the furnaces. On the right side, the joule heated, what you see as the board, it's a rectangular cross section, 1 meter tall vessel. This was joule heated ceramic melter. So both these plants are in operation. And the cold crucible is coming up industrially. This is an experimental setup in which we have done an industrial scale version of the melting. And I'm happy to tell that India is one of the handful of countries, you can count on your fingers, to possess the knowledge of all the three technologies. I don't think I have seen any country having expertise in all the three. Next question will come. So, can we reduce the volumes? Now that we know how to vitrify the waste, can I reduce the volume further? So if you see the glass, the composition of high-level waste, you will find that the fission products and minor actives are a very small portion of it, followed by corrosion products, uranium and added chemicals. So if you can remove the first row, fission products and minor actives separately, you will be able to put more amount of volume in a glass. Because glass has got a fixed, what you call as a waste oxide loading, which is internationally 18 to 25%. This number is fixed. You cannot change this number. So if you are able to remove only the fission products, I can accommodate more volume per glass. And well, is it useful? Is it useful to actually separate? That separation process is what you call as partitioning process. If you see the orange line, if I am taking the spent fuel and I don't do any reprocessing, that is as such from the reactor, whatever it comes, I dispose it. It will take you almost around 1 lakh years, 10 raised to 5, to reach the level of a uranium ore. Uranium ore is naturally available on the Earth's crust. That if you want to achieve on that level, it will take almost 10 raised to 5 years, 1 lakh years. If you are taking the spent fuel and reprocessing, but I don't do any parting. That means all your fission products, added chemicals, corrosion products, if I vitrify all of them in one go, then the time period for reaching the uranium ore level is around 10,000 years. Whereas if I am able to do partitioning, that I am able to separate out the fission products, separate out the actinides, the time period for reaching the uranium ore comes to somewhere around 300 to 500 years. So there is a very good merit in following the partitioning process. There is another schematic, the vitrified product generation in various strategies. So the computation was made on the basis of 1 gigawatt year of electricity, that is 1 gigawatt produced over 1 year. If I follow the direct vitrification route, that left hand side, that is you take all the spent fuel and put it into vitrified it, I will generate almost 7.5 tons per annum, and it goes on reducing. So if you do partitioning, then it reduces by a factor of 2, it's 50% reduced. If I am able to separate out even minor actinides, I am able to reduce it to half a ton. And finally, this is the holy grail. One of my colleagues earlier spoke about transmutation using accelerators. This will come to hardly some 0.1 ton. So this is the last figure is the final, probably the waste management will reach its zenith if we are able to practice the last portion. And we are at least at the stage of the third one, minor actinide partitioning. This is my actinide partitioning flow sheet. So in the actinide partitioning flow sheet, you have first prior pre-treatment called uranium removal. After uranium removal, you will try to separate out anthanide and lanthanides, actinide and lanthanide bulk separation, and then after the group separation. Don't get confused by this. There is enough material available on the literature to do all these things. Only the important thing is this. These require some very specific solvents. One solvent is TEDGA. It's got a lot of words. Basically amide-based solvents. So the making of these solvents are a challenge. So this we have done indigenously. All of them are available within the country, expertise. You can produce this as and when you require. And on the right hand side top is the actual facility wherein this actinide partitioning is carried out. And the bottom slide, we had dedicated this facility in 2013 to the nation, and we are operating the facility. Based on the experience of actinide partitioning, we thought, can we do fission product partitioning? Can I remove cesium and strontium from the waste? So in this plant, we have followed this flow sheet. Again, the main things are the use of calyx crown. The bottom right, if you see, we are using separating cesium 1,3 using what you call the calyx crown solvents, and strontium, lanthanum, and actinide in bulk using what is the thread gas solvent. And right side shows the picture of your separation equipment within a hot cell. Now that we know how to remove the fission products from the waste, actinides from the waste, the next logical question is, can I make some use of it for societal applications? Earlier also we have heard a few speakers from RNC saying that we are trying to use radionuclides from the waste, the free source, rather than sending it to glass, we can use it for some good purpose. So these are the three applications that we have proven and demonstrated and still going on. The cesium, since we are able to remove, we are converted this in what we call as a cesium pencil. Essentially a vitrified cesium which is removed and converted to a small glass canister, glass form, and that has been being used for blood irradiation. I am happy to tell you, almost more than 240 such pencils have been used, supplied to the industry for use as blood irradiation. The second, we have separated strontium from the waste, and this strontium eventually decays to deuterium, which is used for, I suppose, liver cancer treatment. So we are supplying this to RMC, which they use it for as a radiopharmaceutical application. Third is ruthenium also we are able to separate from the waste solution, and we are converting into small silver, coated on silver plaques, which is used for eye cancer. And around 34 number of plaques have been distributed. The last one is important because earlier these plaques were used to be imported from Germany, probably costing a few tens of lakhs. And since we are now producing in-house, so this is being produced at a cost of hardly less than 1 lakh rupees per unit. In addition to the high level waste, I will talk something about low and intermediate level waste also. Since the volumes are higher, the activity hazards are quite low, but the volumes are higher. Hence, management of this is also an important issue to address. And here the main issue is we want to minimize the discharge of activity. That is the primary objective. One of the ways is intermediate level waste is an aqueous waste, for which we have developed the resorcinol formaldehyde resin, which is a highly selective resin. And we know using this resin we have made an ion exchange plant which has been practiced, and it's a very standard technology which is applied all across our reprocessing waste management plants.
Excuse me, Anand. Can you wind up in 2 to 3 minutes? Can you wind up in 3 minutes?
And just another is the treatment of organic waste, for which we have relevant plans. Low-level waste, we follow the chemical treatment route, and the advancements are we are now having zeolites and other forms for treatment and polishing of waste. Whatever waste you are treated, you are generated as the small form, consolidated small form. We have got cementation technologies. Cement is a very simple and a robust process and with good thermal stability. This I want to show you. During the course of the industry, you get a lot of solid waste, a lot of protective wares, tools and equipment. So here we have got 3 solid waste technologies: compaction, wherein the volumes are reduced by a factor of 3 to 5 before disposal. Then incineration, where you are reducing its volume by around 30 to 50 before disposal. And these are the various disposal modules, 3 disposal modules. Depending on the hazard level, we dispose into one of these modules. In summary, what I'd like to say is that India has got more than 50 years of experience in the field of radioactive waste management. The top picture you see was taken somewhere probably in 1970s. It was commissioned in the year 1965. And even so, from that time onwards, radioactive waste management has been practiced and is still going on. And our technology is on par with international best practices. Waste management is a very evolving field. It changes continuously, and we are all in sync with the evolving technologies. The emphasis as on today is to reduce the volume as much as possible, ensure that there is zero discharge of activity, and to concentrate on generating wealth from the waste, that is taking out radionuclides and using for societal application. And we are poised to handle any challenge that arises in the future also. So it's not that I have done all that work. It is the work which are the effort of a large number of professionals. My seniors are sitting here. I'm able to talk here because they are the ones who have done the basic work on which I'm able to present. So large amount of professionals involved in this job. And thank you for your attention and all the best.
Thank you, Anand Gangadharan, for the excellent presentation. Now the presentation is open for discussion. You can ask 1 or 2 questions. Last time when we held a meeting, I had to pay 500 rupees to the students to ask 1 question. I think we have to do that. Okay, if there are no questions, I would like to thank Dr. Anand, Mr. Anand Gangadharan for the excellent presentation. And the waste management is a very difficult subject and you have presented it in a very lucid way. Thank you so much.
Thank you, sir, for the session. Now it's time to express our gratitude. I would like to invite Dr. Susan Epen to present a memento and a book titled On the Wheels of Education Serving USA and India, written by Professor Sree Krishna, a renowned scientist, to Sri Anand Gangadharan.
Move on to the third speaker, that is Mr. Vishwanath, R.V. Vishwanath, and he will be speaking about the fascinating world of rare earths.
Okay. Sri R.V. Vishwanath is currently the General Manager and Unit Head of Indian Rare Earths Limited. He is a mechanical engineer, graduated from Government College of Engineering, Thiruvananthapuram, and in 1990, he joined the Indian Rare Earths Limited in the Chavara unit. After that, he has worked in various other public sector units, such as Neyveli Lignite Corporation and Cochin Refineries Limited. He has had a vast experience as a shift engineer in various production plants and units involving mineral separation, upgradation, and other various maintenance and related projects. He has successfully completed the expansion project in Chavara unit and from basic conceptualization to commissioning, and was involved in every detailed aspect of the project. And later in 2021, he became the unit head, and finally, he is currently the Chief General Manager. The title of his talk is The Fascinating World of Rare Earths.
Very good afternoon to all of you. I am aware that I am standing between the audience and the lunch, so I will try to make it as short as possible. First of all, I would record my sincere thanks to, is it okay? No, I think this mic is okay. So, first of all, I would like to record my sincere gratitude to the organizations, Nuclear Society of India and Atomic Energy Retirees Association and Sree Krishna College, Guruvayur, for making IREL an opportunity to present this before you. And of course, Govindan Gutti sir, he has talked to me about this particular symposium, and invited me to make a presentation. So this is all about rare earths, where the younger community, especially in the, may not be aware of what is rare earths and how Kerala is connected to the rare earths. Can you just look at our daily life? Can you think about without rare earth, communication is possible? Can you, the present way, the social media and smartphones, can you think about without rare earths? And what about the colors? And what about the travel and medicines and medical imaging and power? And today's is era of electric vehicles, and all this goes to the history says in 1909. The history begins with the memories that a German chemist called Herr Schomburg, he has realized that the shiny yellow particles which was sticking to the coir exported from this part of the country to Germany, and he traced and he identified that as monoxide, and he traced back that yellow shiny particles, and he came to Manawalakurichi and Chavara, where he has set up 2 plants to separate monoxide. The requirement was to production of thorium nitrate as GAN, which is used in gas mantles that time in Europe, before the invention or the electricity was not that much popular. So this sparkled the discovery of the vast deposit of monoxide, a rich source of rare earths, a group of elements with wide variety of industry and science. So in 1910, encouraged by the great demand of those days with the thorium oxide in gas mantle, Mr. Schomburg established the first plant at Manawalakurichi and then at Chavara. And later, when at the time of World War I, he was accused as a German spy by the Britishers who were ruling the country. So he was expelled from the country, and with that, all those plants were closed down. And between 14 and 40, there were many companies working in that area in Chavara and Manawalakurichi, and like London Cosmopolitan Mineral Company, Hopkins and Williams, and another one, Travancore Minerals, and another one is called FX Pereira and Sons. So in 1965, IREL took over the first 3 companies, the assets of the first 3 companies, and started producing the monazite and other minerals from the beach and minerals from this one. And FX Pereira and Sons was taken over by the state government, Kerala state government, and currently it is known as Kerala Minerals and Metals. So in 48, as many of these earlier speakers might have shown this photograph of our father of Indian nuclear program. And in 1950, Indian Rare Earths Limited was incorporated in Bombay, and in 51, IREL became a full-fledged central government undertaking under the Department of Atomic Energy, and commenced the construction of its rare earth plant in Udyogamandal in Kerala. Currently, I am working there. The profit earning was only a secondary as against the great role of IRL had to play. This was the words of father of our nuclear program. So in December 24, 1950, the plant was dedicated to the nation by our earlier Prime Minister. And you can see Dr. Baba Bhatnagar, K.R.K. Menon, and Raja Pramukh of Travancore and Cochin, along with second Prime Minister and the Chief Minister of Kerala. This photograph was taken at the time of inauguration. And this was the plant is set up at that time, and now also it looks almost similar. So IRL, the name of the company is now changed to IRL India Limited. Of course, targeting the resources from overseas also. Another company may be setting up like IRL Videsh, which is shortly it will be set up. So currently, these are our present level of operation. Corporate office is at Mumbai, and our rare earth division at Alway near in Udyog Mandal. Then we have a mining and minerals division at Chavara. Then we have a corporate research center at Kollam. Then another mining and minerals division at Manawalakurichi in Kanyakumari district. And we have a rare earth permanent plant recently inaugurated by Honorable Prime Minister. In fact, in last year, it is at Visakhapatnam. And we have a large mining and mineral separation unit at Orissa in Chhatrapur, Ganjam district. And our rare earth and titanium theme park is operating at Bhopal. And this slide shows some of the upcoming projects also, there is a JV signed with the Government of Tamil Nadu and IRL. It is operating at Tuticorin, and Medalam Inayam project at Kanyakumari, that is also coming up. And we have a JV with IRL and a Kazakhstan company for a titanium slag production. And we have another JV at Brahmagiri, Puri, Orissa. So these are the, which is in pipeline. This slide also I have seen in some other presentation, so sorry for the repetition, where IRL comes under the public sector, whereas industrial facilities, heavy water board we have just seen, and the other service sector and R&D. With the Atomic Energy Regulatory Board is the regulators for all these organizations. So our name has changed to IRL India Limited recently, of course, in 2018. And so this slide shows the country's atomic energy program and how IRL is related. The Act is 1962 Act has come, and then AMD is taking care of exploration part. Then the exploitation part, that is mining, processing and refining, is done by IRL, and the metal and alloy is being done at NFC at various locations. Hyderabad is one of the locations, and then it goes to BARC also. Then from there, BARC, the strategic applications starts, and metals and alloys from NFC it goes for nuclear power. So basically the operations will be like this. Ore deposit is there, then we are having a mining segment with a capacity of 10 million tons per annum, and there are about 10 mining leases at the moment granted by various state governments in Tamil Nadu, Kerala and Odisha. And we have a mining and mineral separation segment is there. It's called a pre-concentration and mineral processing with a capacity of 10 lakh tons per annum. And at Chhatrapur in Odisha, Manavalakurichi in Kanyakumari, and Chavara in Kerala. And the rare earth extraction segment, we have a capacity of Ari chloride 11,200 tons per annum, and strategic compound and TSP. Strategic compound in the sense what I said is thorium reserves as well as uranium components. It is at Chhatrapur and Odisha. Then comes the rare earth refining segment where currently I am working. We have a input capacity of 5,000 tons per annum rare earth chloride, and which can produce high pure rare earth compounds to the tune of 2,000 tons per annum, like lanthanum, cerium, neodymium, praseodymium, samarium, gadolinium and dysprosium. It is at Udyogamandal in Kerala. So these are the product mix. We are having these and minerals one side, chemicals and rare earth compounds. Each one I will be explaining what will be the uses and applications. So basically the mineral assemblage will be like this. The BSM will be an ore raw sand, it calls, and then it comes to BSM concentrate. BSM means bit sand mineral, and it contains ilmenite, sillimanite, garnet, which are very high volume presence, but with a low price. And whereas the other low volume is monazite, zircon and rutile. And from the monazite again, the rare earths. Monazite contains three components like rare earths, uranium value and thorium value. And then from the rare earths again all these 17 elements. So the value chain is where the mining, pre-concentration and mineral processing, monazite for captive consumption by DAE. So this is under the control of DAE, and IREL is doing the separation of mining, and then rutile, ilmenite, garnet, sillimanite, zircon. And then it goes for various applications. So this is again under this middle one is, the middle one is under IRA, and it goes to the end users around the 2,000 industries pan-India, which are mostly MSMEs operating in the value chain. It goes for welding electrode, then shipbuilding, titanium slag, titanium pigment, tickle, and then garnet goes for water jet cutting, sillimanite goes for refractory, zircon for opacifier. So this is open to all, the last segment. So this is the stages of mineral separation process up to the rare earth refining, mining, then pre-concentration, then it goes to a mineral separation plant, then electrostatic separation with a magnetic separation, then ilmenite, rutile production is there. Then again a series of magnetic separator, then it comes to a zircon, then monazite and sillimanite, all minerals are separated at this level. And then the monazite goes for the further processing at the attack plant, then leaching and decantation, then active plant where HCl is added, and then precipitation, then NGADU, that is called nuclear grade ammonium diuranate and thorium nitrate. These two are there, and this NGADU or the ammonium diuranate is supplied to DARC for the their test reactors. And the thorium in the form of thorium oxalate is stockpiled for at the targeting the future requirement of the country. And then comes to the rare earth. The third component of the monocyte, I told that it's the rare earth. Rare earth comes to the high pure rare earth plant where solvent extraction we are doing with various stages of solvent extraction. Then all the rare earths, both heavy as well as lighter rare earths, are being refined in our plant. So regarding the activity level, mining will be less than around 4 becquerel per gram. Then mineral processing, where will be a concentration of 180 becquerel per gram. And the monocyte concentration, it goes to 370 becquerel per gram. Then again, RE side, it comes down to 1 becquerel because the monocyte concentration, uranium and thorium, being separated out. Then it comes to the RE refining and RE metal or RE magnet. There the activity levels are considerably low. So these are the physical properties by which we separate the various minerals. Ilmenite is mostly conducting and magnetic, whereas rutile is conducting but non-magnetic. Then zircon is non-conducting, non-magnetic with a specific gravity difference of 4.6 to 4.7. And sillimanite, it is non-conducting as well as non-magnetic, but the specific gravity is slightly below zircon, and monazite is non-conducting and feebly magnetic. And as I told that monazite is a combination of thorium, uranium and rare earth values. In fact, it's a phosphate. And I think I will skip this. It's not much relevance, but this is about the country's the nuclear program, which would have been explained here earlier, like 3 stages, pressurized heavy water and fast breeder. And here the third stage is the thorium-based reactors, for which we are now currently stockpiling all the thorium values available in the country. Like zirconium and hafnium and thorium are very important strategic elements. Those, again, that 3-stage our program, nuclear program. So here comes the rare earths. Rare earths are a collection of 17 elements, namely including scandium and yttrium and the lanthanides. Lanthanides contains 15 elements plus scandium and yttrium, and so they are called rare earths, having multiple application, and it is called the vitamins for the modern industry. Why it is called? Because vitamins we only consume very small quantities. Like rare earths also, we require very small quantities, but it will definitely enhance the performance. Like it is technological superiority and incorporation of innovation to meet the challenges and miniaturization. So the applications starts from magnets, and then in defense, nuclear, metallurgy, phosphors, medical, catalyst, space, everywhere it is finding application, including glass. So this again, the periodic table shows the scandium and yttrium, then this lanthanum series. Out of that one, lanthanum to gadolinium, it is called a lighter rare earth, and terbium to lutetium, it is called a heavy rare earth. So these are some of the applications of rare earths. The picture itself is self-explanatory: nuclear, e-mobility, high technology devices, storage devices, wind turbine. Again, these are the dysprosium, residuum, neodymium, and samarium. Its applications in defense, nuclear energy, and wind turbines. These are the lighter elements are also having a lot of applications like communication, control roads to magnets, permanent magnets. And medical, lot of applications are there. The dental crown, daily life applications for the titanium. And defense and aerospace. The petroleum cracking, lanthanum, we know that longer chain hydrocarbons are cracked using lanthanums as catalyst. So these are again coming to various vast uses of lanthanum. And this is one of the interesting for the MRI contrast media. Gadolinium is used for the magnetic resonance imaging. And these are the latest applications for the neodymium and iron boron magnets and samarium cobalt magnet. In fact, IRL has set up a plant at Visakhapatnam with the BARC technology and DMRL technology for production of samarium cobalt magnet. Mainly it is used for the defense applications. And again, magnets for the electric vehicles. So the rare earths finding a lot of application, not only in magnets and other places in an electric car, like glass and mirror polishing is done with the cerium and LCD screen, europium and yttriums. Again, cerium is used, and a lot of sensors are using yttrium. Electric motors, I have told that now permanent magnets, miniature permanent magnets are used. In a car, almost 25 motors electric where the permanent magnets are being used. Then, of course, catalytic converter for emission control in cerium and lanthanum for a car. So, in automobile, a lot of applications.
Excuse me, Mr. Nath, can you wind up in 2 minutes?
Yes, yes. And green energy, again, this one. And magnetic resonance imaging, we have already discussed. And this is what I was telling earlier, that in a mobile phone, you can see the magnets are used in vibrator, color screen, glass polishing, then speakers for the magnets, circuit boards, electronics, everywhere we find rare earths. Other elements are there, and these are the heavy rare earths. Recently, our plant is producing with 4.9 purity, that is for the reactor application. It is then it's a neutron absorption in a moderator. It is gadolinium and dysprosium. These two are used there. And dysprosium is finding application in magnets again. This is also 3.9 to 4.9 purity materials are being produced. Military applications like guided missiles, smart bombs, unmanned defense aircrafts, and other defense applications. I will quickly go through all these laser targeting, all those things. Sonar transducers, and ilmenite. It is the production for the titanium pigment. This is the whitest element ever discovered in the world. It goes for a base for the paints and colors. And then skincare, cosmetics, medicines, toothpaste, and this is one of the challenges. It is called prosthetic limbs because of its compatibility with the human body as well as strength. It goes for the titanium alloys are used for the fighter jets and turbofans and aircraft bodies and our space vehicle bodies for the heat resistance, lightweight. Rutile mainly goes for welding electrode. Zircon for mainly goes for ceramic tiles. These tiles place then for dental crowns, then precision casting, and yttria stabilized zirconia is used in the thermal barrier in afterburner for a fighter jet. Sillimanate mainly goes for refractory in steel industry. Garnet is mainly used for water jet cutting, shipbuilding, and we are actually governed by this rule, atomic mineral concession rule, which we are being empowering to do the mining and mineral processing. And, so this is the heat sand mineral harvesting, the photograph taken from the Chavara coast. And this is the dredge mining we are doing. This is the mined out, and after refilling we are afforestation is being done. So, from morning to evening, education, livelihood, military mission, space mission, so the entire future requirement of the energy requirement. So, we are for you every moment. And for the national security, these are our plans. This is the Chavara plant, the first one is Rare Earth plant, and this is Manavala Kurichi, and that is the POSCOM, Orissa. Thank you for the question.
Thank you, Mr. Vishwanath. You have really taken us to the real world of rare earths. It was very fascinating. But now it is open for discussion. Yeah. Any questions? Yes.
Yes.
Please.
China currently has a monopoly on rare earths because it reduced the cost so low that all other companies are now destroyed. I mean, very weak. So how is India holding up in the global market of rare earths? And are we able to meet domestic production? And how is rare earths market in India economically?
Very interesting question. The rare earth market, as you know, is currently being controlled by China because world's reserve, about 35% of the world reserve is in China. We are having only 6% reserve. Above us, Brazil is there, and we may be in the third or fourth position. But as you are aware, this China is now currently controlling. But China was coming into this field very recently. Recently means after 1990. Till that time, they were not knowing this one. But the Chinese reservoirs started explored in after 1990, and now what they are considering is that like Gulf countries are having petroleum, China is having rare earths. So they are actually dominating the market. Of course, we have our own limitations with the monazite as our feed material or a raw material.
Are we able to meet domestic demand?
Yes, we are. IREL is committed to meet the domestic demand. In fact, we have certain limitations in this technology, like in our country, I am telling about, because we are closely associating our operations with BARC. We have mining, we have enough capacities. mineral processing we have enough capacities, and we have in between we have monocyte processing we have enough capacities, no doubt, but we have lacking capacities or technology in rare earth conversion of rare earth oxide into metals. Currently BARC and IRL is closely working for that one, but again from metal to magnet we have capacities. So in between there is a gap. We are actively working on that one. In fact, our mandate given by the Niti Aayog and the Prime Minister Modi ji is that by 2030 we should be able to produce 13,000 tons of RU, rare earth oxide. That is the mandate given to IRL. So we are all working for that one.
Thank you.
Thank you.
Any more questions? If there is no more question, I would like to thank Mr. Vishwanath for the excellent and fascinating presentation on the fascinating rare earths of India. Thank you.
Thank you.
Thank you, sir. Now it's time to express our gratitude. So I'd like to invite Dr. Susan Eapen to present a memento and a book titled On the Wheels of Education, Serving USA and India, written by Professor Sree Krishna, a renowned scientist, to Sri R.V. Vishwanath. Thank you, sir. Now to honor Dr. Susan Eapen, chair of this session, and Dr. Padmanabhan, co-chair of this session, let me invite Dr. K.V. Das to present the mementos. Sir, please.
Now it's time for lunch. Please enjoy the break and we will reconvene at 2:15 for the next session. Lunch for the students is provided at 51M on the ground floor. Students are requested to be there with their coupons.
Welcome back, all of you, to the session. Hope you had a wonderful lunch, and now we are moving to the next session by Dr. Susan Epen, retired senior scientist, BARC, adjunct professor, Bioscience Group, Union Christian College, Alua, on the topic Nuclear Technologies for Feeding the World. And this session is chaired by Sri Anand Gangadharan, Head Waste Management Division, BARC, and co-chaired by Dr. Niranjana Emma, HOD, Botany, Sree Krishna College, Guruvayur.
Hello, good afternoon. So I hope everyone had a sumptuous lunch. So we have in one session only one speaker. Dr. Susan is there on the topic of very good assimilation of physics and biology, nuclear applications in bio and agriculture. I request Dr. Niranjana to give a brief introduction about the speaker.
Thank you so much, sir. A very warm good afternoon to one and all. It's okay, ma'am. I'll just give a brief introduction. We know, sir. Sure. So, a very good afternoon to all. We are in for the final session of the Symposium NEST 2025. It's my privilege to introduce the resource person for the session, Dr. Susan Epen. I believe she is a representative for women for science and women in science, especially in this symposium, because I see her name, the only women in the list. Ranked among the 2% of world's top-ranked scientists in plant biology and botany by University of Stanford since 2020, she has retired from BARC in the year 2011, heading the plant biotechnology division. She has pioneered in the area of transgenic plant research and secondary metabolite production. She has about 140 plus publications to her credit and impeccable participation in national and international deliberations. Present, she is working as an adjunct professor in School of Biosciences in UC College, Alua, which is a proof that she is still involved in motivating scientific temper in the present day academia. On behalf of Sree Krishna College, we are blessed to have you, ma'am, in this session, and welcome.
Good afternoon. Can I have the first slide? Yes. Most of you must be a physicist or a chemist, and I don't know how much of biology you know, but what I am speaking today is very simple biology. Actually, there is not much of science also in that, so it's very easy to understand what I am going to speak. The topic for today's presentation is nuclear technology for feeding the world. Next slide. Our world population is increasing, and today, that is in March 2025, the current world population is 8.23 billion, and in 2050 it's going to reach 10 billion. So there are more mouths to feed with less land and under changing climatic conditions. The Indian population with 1.46 billion has taken over China. We are the most populous country. Next slide, please. So I'll be speaking about Department of Atomic Energy's contribution towards food security. I will touch only two topics, that is crop improvement and food preservation. Next slide, please. Our major crops in India are cereals and millets, then pulses or grain legumes, then oil crops, vegetables, fruits, and other crops. There is no pointer, so I cannot show it each one of them. Next slide. So 2023 was declared as the year of the millets. Do you know what is the advantage of having millets? Millets need less of water, less of nutrients, and they can withstand under high temperature. And also, they have very good properties. They are high fiber, high anti-diabetic properties, good for heart patients and other patients, and they are crops for the future. They are the superfood. We have pearl millet, finger millet, little millet, foxtail millet, proso millet, etc. Next one. Time, you are taking time. Now crop improvement in Baba Atomic Research Center has focused on oil crops. Now we are importing some of the oil from abroad, and the important crops that we are working on are groundnut or peanut, mustard, Indian mustard, then soybean, linseed, teal or gingerly, then sunflower, and then we have grain legumes, important grain legumes like mung bean, urad bean, pigeon pea, cowpea, rice, then cereals like rice, wheat and sorghum. Next slide. And recently we have released about 8 varieties in the year 2024 in October, and the varieties were dedicated to the farmers of India because they are the backbone of our agriculture. So the oil crops we are working on are groundnut, mustard, soybean, sunflower, linseed and sesame, whereas the grain legumes are mung bean. Mung bean you all are familiar, that is cheruvayar. Then urad bean is urad dal, that is udana. Then pigeon pea is one which you use for dal or sambar. Cowpea is a vegetable, chickpea is the kadala, okay? Now we are coming to cereals. We have rice, wheats and sorghum, and then there are other plants like banana. Next one. What are the methods of crop improvement? There are several methods of crop improvement. One is selection. You have a field in which your rice plants are growing, and suddenly the temperature has gone up. So you go to the field and find out a good plant which is surviving under high temperature. You select it and then multiply it, that is selection. And do you know what is introduction? You have a field of rice plants and you want to have a better variety of rice. You bring it from some other field or from some other country. So do you know that in early 1950s, 60s and all, India faced a lot of hunger. There was a insufficient amount of rice and wheat to feed Indian population. And all the countries were laughing at us and they said, India is standing with a begging bowl, and we used to import wheat and other things from United States. So at that time, M.S. Swaminathan, who was a director of Indian Agriculture Research Institute, and C. Subramaniam, who was a food minister and a Borlaug from Mexico, they decided to import a wheat variety to India. So in 1960s, one wheat variety, which is a semi-dwarf variety, was brought to India. It had a particular gene called RHT gene. And then it was crossed with our Indian varieties, and we produced Kalyan Sona, Sonaliga, etc., which could withstand, lodging. Lodging means when the plant is very tall, it has a tendency to fall down. But these plants were shorter, they were sturdy, they had high photosynthetic ability because they had this RHT gene in that. So we could improve our yield, and our Punjab farmers in Punjab, where wheat is a main crop, they were very much interested in that and multiplied it, and we, instead of standing with a begging bowl, India became a land where wheat is produced in surplus. And similarly, in case of rice also, there was a shortage. I don't think you all are millennials, and you may not be knowing that, we had to actually observe fast on one of the days. I don't know which day, in a week. Lal Bahadur Shastri has said you should not eat on one particular day. So we were not eating in the night on one of the days because food was not there. Then a rice variety was imported. It is known as Teichung Native 1, and it was crossed with our Indian variety, and we produced shorter variety with improved yield and other characters. So this is the next one is mutation breeding. Although all these techniques are being done in BARC, I'll be speaking only about mutation breeding because we are using nuclear technology in mutation breeding. The area in which I was working is genetically modified plants. I'm not going into that. Then recently, the new technology is gene editing. You can precisely modify one single nucleotide in the DNA. Next one. So I am only going to speak about mutation breeding. You all know that plant cells or animal cells, they have got a DNA in them, and in the DNA there are several genes which determine the yield and disease resistance and different characters. So what we do is, you can induce mutation. Mutation is a heritable change which will be passed on from generation to generation. So physical and chemical mutagens can be used for induction of mutations. We are studying only on radiation-induced mutagenesis, gamma rays, X-rays, and electron beam can be used for induction of mutation. First, before doing any experiment, you have to fix the LD50 dose. That is a dose selected, and that after selecting the lethal dose for killing 50% of the population, you select one or two doses for irradiating your tissue for induction of mutations. Next slide. In nature itself, we see mutations, like due to evolution, mutations are there, and due to evolution, some of the mutations are selected. That mutation frequency, however, is very low, maybe 1 in a million, but with radiation, we can enhance the frequency of induced mutation to probably 1 in 1,000. The frequency of mutations are enhanced, but most of the mutations induced by radiation or with the chemical mutagenesis, they are unwanted, deleterious mutations. But when the plant breeder has to select the desired mutant from the mutant crops. Then in the case of grain legumes, for irradiation, seeds are being irradiated. But you know that there are two sets of chromosomes. I don't know whether you all are physicists, probably. There are two sets of chromosomes, and only dominant gene will be expressed in the first generation. But we are also interested in the recessive gene, which will be expressed only in the second generation after irradiation. That is called as M2 generation. But whereas in case of vegetatively propagated plants like sugarcane, potato, etc., you have to use cuttings or bulbs or whatever for irradiation. Next slide. So mutation breeding, what are we looking for? Yield parameters. You want to improve the yield. Actually, yield is a very complex character. It's not a single character. It's a quantitative character. Then biotic stress, you know that in present time, there are a lot of diseases and pests which attack our crop plants, and it will bring down the yield. So tolerance to biotic stresses is very important. Tolerance to abiotic stresses. Our climate is changing and our earth is subjected to drought, high temperature, salinity, alkalinity, and our plants cannot produce their yield under these conditions. We have to select mutants which are tolerant to abiotic stresses. Then currently people have the ability to buy good quality food, so they are very choosy in buying food. They are very much bothered about the nutritional quality of the food, micronutrients. You want zinc, you want iron, you want vitamins, you want to change the oil composition so that it will suit your heart better. So next slide. So what we do is, suppose we are irradiating rice or wheat, the seed is taken and it is irradiated in a gamma chamber or subjected to X-rays and raise the first generation, that is called the M1 generation, and the second generation called M2 is raised, and there only screening is done for the mutations. Then once a mutant is selected, for example, disease resistance, disease to fungus, suppose it is selected, you carry forward for 3 to 4 years in our division only, or in our field only, in BRC, next one, or you can take the mutant and cross with our Indian other good varieties also. Next slide. Then it goes for a state agriculture university. BRC has many collaboration with the state agriculture university, like even Kerala Agriculture University, Tamil Nadu Agriculture University, Akola University and Akola and all that. So after that 4 to 5 years, it is going for central release in a given particular zone, then goes to notification in Gazette. It will take 1 to 2 years. Finally, it goes to the Ministry of Agriculture and it will be released. So once you get a mutant, minimum it takes 10 years for the variety to be released. Next slide. Next slide. So let me come to the oil crops. The most important oil crops in which BRC is working, they are groundnut, Indian mustard, kadaga, linseed, then soybean, sunflower and teal. Next one. In groundnut, it's a very important crop, and we have produced lot of mutants, and we have released them into the market, like they were, because they are cultivated in groundnut is a very important oil crop, especially in the north, and it is cultivated in 5 million hectares with 27% of oil seed. And objective is to improve the yield. Wherever we are working, we want to improve the yield. We want bigger seeds. We want early seeds, early maturing seeds with a better shelling capacity, with higher oil content, improved oil quality, high oleic acid, tolerance to biotic and abiotic stresses, then better oil shelf life. And X-rays, gamma rays, an electron beam also being used for inducing mutations in groundnut, and about 20 varieties of groundnut were released and given to different states and grown in different parts of India. TG1 is one of the earliest large-seeded variety developed from Spanish improved. For Kerala, we had released TG3 for Kerala and Odisha. Next one. And we were looking for a high yield seed dormancy. Do you know why we need seed dormancy? Because suddenly a rain comes, the plants, the seeds in the groundnut will start germinating, which we don't want. So the seed should be dormant for some time. Then drought tolerance, then better oil quality, higher oleic acid. TG39 is an example of all these things, and several millions of TG varieties were traded, and our foreign exchange has gone up like anything. Next slide. So these are some of the varieties which were released in with radiations. TGK19A, it is a large seeded one grown in Maharashtra. Somnath or TGS1 grown in Gujarat. Then TG22, TG24 is a very important variety grown in Maharashtra, Karnataka and West Bengal. TG39, then TG45, TG47, TG26, TG37A, TG38, TPG41, TG51. Next slide. They are very important varieties, and here is the latest variety, that is TAG73. It is a gamma-induced groundnut variety. It is released in a collaboration with Junagadh in Gujarat and also with Akola, PDKV Akola. It matures in 105 to 110 days. And usually if you break a groundnut, you get 2 seeds. This is mostly 3 seeded. So yield is higher. And you can see the graph there. The TAG is going into the details. For example, TAG24, it is being grown in Gujarat, Karnataka, Maharashtra, Rajasthan and West Bengal, and it has got higher harvest index, better water efficiency, and yield is also quite high. And TG37 has drought tolerance and wider adaptability, and grown in Gujarat, Rajasthan, UP, Punjab, Haryana, Orissa, West Bengal, Bihar and northeastern states. And another one, TG39, is also large seeded, high oleic acid, and grown in Rajasthan and Karnataka. TG51 is also having a good early maturity in high shelling percentage, grown in Odisha, West Bengal, Bihar and northeastern states. Next slide, please. These are some of the farmers along with the groundnut crop in Andhra Pradesh, Rajasthan, Karnataka, Gujarat, West Bengal, Maharashtra and Uttar Pradesh. Next one. Now we move on to Indian mustard. I know in Kerala people don't use rye or Indian mustard, but it's an important crop in the northern part of India. Next one. Indian mustard, that is Brassica gentiana, 12% of world population, out of that are using this. 6.27 million hectares in India are under cultivation of this particular crop. And in BRC, wide spectrum of mutations for morphological, yield parameters, etc. were released plants with yellow seeded ones with more oil, more protein also were obtained. You can see the yellow seeded one has more oil compared to the black seeded mustard. And two scientists from Kerala, late Dr. Gigi Nair, he has worked on production of this yellow seeded one. And then Dr. Verghese Abraham, we had been to his house 2 days back. He's also worked on this. Then Jumbolkar and many people have contributed to this new varieties of Brassica genetia. Next one. So TM1 is a yellow seeded mutant. Then TPM1, TJD1. This is a very famous variety, high-yielding variety called Varuna. And from Varuna, using gamma radiation, these two varieties were developed. TM2 and TM4 were released in Assam, whereas TBM204 were released specially for West Bengal. Several early maturing varieties are being grown in advanced stages in different states besides all these. Next one. So TBM204 released in 2019 for West Bengal, THPM1 in 2022 for Himachal Pradesh, BBM1 in 2022 for Jharkhand, TAM108 for Maharashtra, TBM143 in 2023 for West Bengal. Some of them are yellow-seeded ones. They are disease resistant, they have disease resistance, they have drought tolerance, and they have high yield, yellow-seeded nature, and they have high oleic acid. Next one. Next comes soybean. All of you are familiar with soybean. Soybean is one of the crops which is not only a source of oil, but also a source of protein. Among plants, soybean has the highest protein, maybe about 40% comparable to the meat, but the yield is very low. So in BARC, some varieties like TAMS 38, TAMS 9821, with a superior seed yield, non-pod shattering, and resistance to diseases and pests were developed and grown in Maharashtra. They are tolerant to biotic and abiotic stresses. They have got a low trypsin inhibitor. What is the advantage of having low trypsin? It's an anti-nutritional factor. So it's a low in these new varieties, it's low in phytic acid. What does phytic acid do? Phytic acid will stop absorption of some of the micronutrients like zinc and iron and all that. So it's low in phytic acid. It has got an altered protein profile, altered fatty acid content, high harvest index. Next slide, please. This is linseed. Objective is that the linseed can be used for two purposes. Now you can use it for edible purposes and also for industrial purposes. When there is high linolenic acid, you can use it for industrial purpose. When linolenic acid is low, you can use as a edible oil. So TL99 produced by gamma rays were released in Assam, Bihar and Jharkhand. The variety is the first edible oil variety. It is moderately resistant to powdery mildew and alternaria blight and all diseases. Wilt is fungal disease, rust is a fungal disease, so they are resistant to bacterial and fungal diseases. Next one. So this is a Trombay linseed variety, TL99. Released in UP, Bihar, Jharkhand, West Bengal, Assam and Nagaland. TL99 is the first variety which is used as a source for edible oil. Otherwise, it is used only for population in India are vegetarian and they cater to the population in India are vegetarian and they cater to the protein requirement of Indian population, right? They are also called as grain legumes. Let us go to the next slide. The important source of protein very important for the vegetarian population of India, and they should be resistant to pests and diseases, abiotic stress, then physiological and biochemical traits should be improved. Now you all are familiar with the green gram, that is a mung bean or chiruvayar. It is subjected to gamma rays and electron beam for production of mutants. Then black gram or urad dal, urad is subjected to gamma rays. Then pigeon pea is tur you will use used for sambar and dal. Then cowpea for as a vegetable. Chickpea is a kadala or a deshi type or a, kabuli type. Then cluster bean, another one. Next one. So these all were irradiated and the mutation breeding was done. Next slide, please. Please move fast. Yeah, here comes urad bean or black gram. I'm sure that some of you would have taken today morning for breakfast either idli or dosha or masala dosha or vada or something. And all these have come from TU40, which is a variety released in South India, especially in Tamil Nadu and Kerala. There are other varieties of urad bean, TAU1. Next one. So it shows how important it is to have new varieties, high-yielding varieties. This is another high-yielding varieties released to Madhya Pradesh, Trombe Jawahar Urad Bean, or black gram variety, TJU 130 and TJU 339 were released and notified in Madhya Pradesh. It matures very early. It has high protein, resistant to many diseases like virus disease, anthracnose and powdery mildew diseases, bacterial diseases, and yield is quite high and people are very happy with the TJU 130 and TJU 339. Next slide, please. Now comes our green gram, mung bean, that is cheruvayar. It has got a large size compared to what we normally eat. It is resistant to virus, that is yellow mosaic virus, released to northeastern plain. And another one is pigeon pea. Pigeon pea is a dal. TJT 501, 60% of Madhya Pradesh, this variety is being grown. In PKV Tara is grown in Maharashtra under drip irrigation. Next slide, please. So this is the TJT 501 pigeon variety being grown in Madhya Pradesh. It is high yielding, 20 to 30 days earlier than, how much time? 5 minutes. I'll take another 2-3 minutes more. Okay. So 20 to 30 days earlier than traditional varieties like Durga. It is farmers can even grow a second crop. 60% of the MP farmers, 60% of the land in Madhya Pradesh are being grown. This plant is being grown there. Next slide, please. This is a Trombe variety, TC901. It's a cowpea variety, high yielding. Next one. Next one, these are the Trombe pulse varieties. I'm not going into the details. Next comes, pulse crops. We have released, 8 mung bean varieties, 5 urad bean varieties, 5 pigeon pea, 2 cowpea varieties. Out of 56 varieties in with which one? Pulse crops, 20 varieties are released by mutation breeding from NABTD BRC. Many varieties are higher in yield. Now, next one. So now we move on to cereals and millets. You know cereals, how important they are. So we have developed varieties which are resistant to diseases and pests, resistant to soil alkalinity and consumer preference also. Traditional varieties are very late maturing. They are not good yielders. They're large, they fall down due to the tall structures. Next one. So some of the varieties which are released are climate resistant. They can stand in high soil alkalinity. They are resistant to diseases and pests. And first variety released was in 1988 because one of our colleagues called Narahari had developed it. So it's called Hari. Then TCDM1 2019, it was released to Chhattisgarh. TKR column was released in Maharashtra. Bikram TCR, why it is called Bikram? Can somebody tell? For Sarabhai. Sarabhai was our chairman, maybe in up to 1971, and also the director of BRC. So Vikram TCR in Chhattisgarh, Javapul in Chhattisgarh, next one. This is rice, then wheat also, many varieties are released, and several varieties are recently released, like Bona, Luchai, then Trombe, Kongan, Khada, etc. This is wheat, rice again, next one. Rice, different varieties, TCDM1, Bikram TCR, 2022 TCVM, 2022 TKR column in Maharashtra. They are doing all very good. Next one. Now wheat varieties, 2 new varieties like Raj Vijay, wheat 155, this is notified. Then there are other varieties also. Next one. Now we come to sorghum. Sorghum also one good variety called TAKP S5 called Suruji was released with Akola with Deshmukh, Punjab Rao Deshmukh, Krishi Vidyapith, Akola. They are high yielding plants. Next slide. So these are some of the things. I'm not going into how many plants are there. Totally 70 mutants are coming in the market right now. And one more is notified. I think maybe next year it will come, that is banana. Next one. So this is grown all throughout the country. The plants are being grown. Mutant plants by irradiation are being grown. Next one. I will also speak about food preservation. That is from my food technology division on preservation of food. You all know that we have a large population. Although we produce lot of food, most of the food is lost during transport or within 2-3 days or within 1 or 2 months because of insect pests, bacteria, fungi, etc. Next one. So this is a food irradiation technology for food preservation. Next one. Multiple uses. You keep a potato for 2-3 months, or you keep an onion for 2-3 months, they start germinating, for sprouting. So you can prevent sprouting by radiation. Then you keep grains for some time. There will be infection by bacteria, by fungi and other things. You keep fish and other things. Within 1 or 2 days, they will get damaged. Then these can be disinfested by radiation. Mango. So some of you cut open mango in the month of July. You might have seen some insects inside, right? Have you seen insects? Yes. How do they come inside? When they're flowers only, they lay eggs and they germinate. They come out as insects when the mango ripens. So when we are transporting this mango, especially to USA and all that, these insects are traveling without any visa to USA and all that. They don't need any visa. So America was objecting, and they came to BRCs quite some time back because they were very fond of our Alfonso mango. They don't get that Alfonso variety over there. So they used radiation. We use radiation for irradiating these mangoes, and then we transport it not by plane but by ship, because it can stay for a longer time, no insect inside. Even, near BRC in Navi Mumbai, we have a plant for cleaning up, for using radiation for spices and fresh, not fresh foods. All these spices. Kerala is a source of spices. Even, Vasco da Gama came to Kerala all the way in a long time back for spices and discovered India, came to India. But, these spices are not irradiated here. It has to go to Bombay or some other place for getting irradiated for sterilization. The shelf life extension, then the insect infestation, hygienization, etc. can be done. Next one. Now comes how much of food is lost, India is a populated country. 20 to 50% or 30 to 50% of fruits and vegetables and grain products are lost. Meat and poultry also lost. So we can use radiation for improving our shelf life, improving their shelf life, and also for disinfestation. Next slide. World, who says radiation is safe? Is not BRC saying. WHO says, then you can all believe. FAO says. IAEA says it is safe. Next slide. Then before releasing using the radiation, all these studies have been done. Dr. Surendranathan knows very well. There should not be any radioactivity. There should be microbiological safety. Nutritionally, it should be same as before. Absence of toxic substances. And you do multi-generation testing, not just one generation. You grow mice and give irradiated food, and for 10, 20 generations you study rat, guinea pig, cat, dog, even volunteers. Some of you might have eaten irradiated food, as volunteers. We have taken in our canteen. Next one. So advantages is highly effective. There's no residue. Otherwise, what do our farmers do, or our merchants do? They put a lot of pesticide on our fruits, isn't it? But without all this, there is no pesticide, no chemicals on that. And pre-packed commodities also can be used. It goes inside the tissues and sterilizes it. But the thing is that all commodities cannot be sterilized by this technique. It is capital intensive. I don't think Kerala has a plant for sterilization of food. Next one. This is gamma chamber with cobalt-60 and cesium-137 as a source. Next one. Then we have X-ray machines. Next one. Electron beam. I think sir has already spoken about electron beam. For next one, this is a gamma radiation facility. Next one. These are some of the irradiation facilities available in India, but nothing in Kerala. Next one. Then this is near Navi Mumbai. In Navi Mumbai, a plant, radiation processing plant in Navi Mumbai for sterilization of onion powder, chili powder, curry powder, turmeric powder, coriander powder, sambar masala, mixed masala, Ayurvedic product, cosmetics, pet food, etc. Next one. And this is our place called in Lasalgo, near Nasik, we grow potato and onion. And keep onion for 3-4 months, it starts germinating, sprouting. Sprouts are inhibited by irradiation, it is packed in gunny bags, irradiated and, transported. So suddenly the price of onion may not go up, if you store and store properly. Like suddenly the price of onion goes up maybe up to 100 rupees, 120 rupees, etc. This will not happen if you irradiate and store them. Next one. Then we have a turmeric. Look at the turmeric on the other side. Turmeric which is irradiated, and this one, pepper which is irradiated. Non-irradiated, they have become already damaged by maybe by insect or by bacteria or by fungi. Next one. Mango. Mango is being exported. You are saving so much of money. In 2023, 2,500 metric ton is sent to USA alone. Think of the economy. Next one. Now comes electron beam. This is not electron beam. Vegetables, fruits, flowers also can be irradiated. We can look at the non-irradiated and irradiated onion, how it is sprouting, potato irradiated and non-irradiated. Next one. Now comes the mango. Next one. And you can even use electron beam. Electron beam is very highly acceptable because it is a controllable. You don't have to shut down the thing, and you can use throughout, less costly. Next one. This is electron beam irradiated grains and onion after 5 months after irradiation with electron beam. Next one. This is a paper cutting. Next one. You don't have to get scared of radiation. This is much, much better than chemicals which are sprayed in our fumigation of grains and vegetables. Next one. Throughout India, throughout the world, it is being accepted in 60 countries, including India. Next one. Now let me tell, I wanted to speak to something more, but I'm not going to that. So this is sterile insect technology. Lot of pests and all come and eat our grains and other fruits and vegetables and all that. So what technology is being developed in BRC is called sterile insect technology. We take the insect and rear them in the laboratory so that there will be lot of insects. Out of that we separate the male insects and sterilize them. And then you can take the sterile. Sterile means they don't die, but they will be sterile. So they will be taken and sprayed in the field, So all these insects come into the field. Remember, they are male insects, but they are sterile. They go to the wild and mate with the female insects, and there is no progeny because they are sterile. So this technology BRC had developed. I didn't get any slide recently because next one. This is previous one. This is a technology developed for an oriental fruit fly called Bactocera dorsalis and melon fly, and it is used in UAS, University of Agriculture Sciences, then Raichur and plant at different regions in Maharashtra. This is SIT, sterile insect technology, where male insects are sterilized and released into the atmosphere, and they mate with the female and resulting in no offspring, so that insect population is controlled. Next is the last slide. Are you familiar with fungal infection in plants? Plants are subjected to many fungal infection, and using one fungus, while like people are fighting with each other, fungi also fight with each other. So there is a fungus called Trichodoma virens which can kill other fungi. You know how it kills? The fungal walls are made of chitin. So it produces chitinase, it produces glucanase. It will go and kill all the other, like a pathogenic introduced into tomato plants, introduced into brassica plants, and some glucanase into, and then plants were resistant to fungi. I am not touching that because it is not a direct application of nuclear energy. I am only talking about how this fungi was mutated, and it's a better, more efficient fungi to kill other fungi. One fungi fighting with other fungi and killing other fungi. So I will stop this because there are other technologies also, like a soil, for a soil health, for water efficiency. There are many technologies using radioisotopes, but I am not stopping here. Thank you so much for your attention. Good suggestion.
Just say, I just talk.
Good suggestion. Maybe 40, 50 people have worked maybe for several years, and these are the result of their variety. These are the result of their hard work. And after that, it has to go to several university trials, then state university trials, then gazette trials and all that. So enormous amount of work.
Excuse me, so maybe we can have the discussion later on. Yeah, yes. Anybody with questions? So final.
It's actually two questions. First question is, we are actually exposing our fruits and plants to ionizing radiation. Ionizing radiation means that it will rip the electrons from the atom's orbit. So doing that will also damage the DNA, right, of the plant. So won't that cause any adverse effects That's the first question. Second question is that when we do irradiate several food things like that, and not every bacteria or everything will die. Some will remain, right? And they have the potential to develop as radiation resistant bacteria. There was one study in America where a lot of cans of chicken, canned chicken were exposed to large amounts of radiation, and they discovered a bacteria which could resist radiation entirely. So won't it create new variants as well?
It can create new variants. For example,
radiation-resistant bacteria.
Yes, it can create also. You know about one bacteria,
Radioduranos.
one Dinococcus, now it has got something else.
That's it.
One of our colleagues from food technology, Surendran's colleague, Dr. Lewis, he had isolated from what fish? Bombay duck fish. It's a fish, highly radiation resistant bacteria, no? Now it is called micrococcus. Dinococcus also it is called. Now it is used, for radiation studies. What it can do is it can, after the DNA breaks down, and after that it can recombine. I think one section, Dr. Apte's section in our department, started working on this again after 30 years after Dr. Lewis had discovered this particular one. What was the other question you said?
Ionizing radiation, won't it damage the DNA of the
it
plant?
It will affect. That's
So
why it's not
won't that affect?
It won't affect us. It won't affect us.
Okay.
But there is no radioactivity in that. That's why so many studies have been conducted before releasing the technology.
Okay, thank you.
One final comment.
I just wanted to make a comment about Dr. Bhaskar Mundayur's suggestion of changing the label. Years back when I was, before my retirement, there was an occasion when I had an opportunity to interact with Mr. P.J. Joseph and Francis George. That time I tried to promote the idea of having a spice irradiator somewhere near the harbor of Cochin. And they came to BARC and discussed with the Dr. Banerjee. That time he was the director, Bhattacharjee, he was the director. And they discussed and finalized plans and went there and tried to, establish a irradiator, spices irradiator in Kochi. Where myself and few others, including Director Biomedical Group, happened to go there. Then we found out that there was few others from the ethylene oxide lobby. They said they somehow impressed the authorities, including P.J. Joseph, that this is very dangerous. And moreover, moreover there is a, linear accelerators, which is not at all harmful. That time there was no technology. I mean, Indore was just about to begin, sort of. They told all that and rejected the proposal, to be in short. So label is not the major reason. It is the only reason is the business community, their interests. Ethylene oxide, they wanted to, that preservative, they wanted to continue with the chemicals instead of having radiation. Thank you.
It is something like that nuclear reactor not being in Kerala but in Kudamkulam.
So I thank Dr. Susan for an enlightening talk. Thank you, madam.
Thank you, ma'am. We had a variety session. Now it's time to express our gratitude. So I would like to invite Sri Anand Gangadharan to present a memento and a book titled On the Wheels of Education, Serving USA and India, written by Professor Sree Krishna, a renowned scientist, to Dr. Susan Ethan. Thank you, ma'am. And now, to honor Sri Anand Gangadharan, chair of this session, and Dr. Niranjana Emma, co-chair of this session, let me invite Sree Krishna Prasad, Awareness Committee Member, ERA, to present the mementos. Please, ma'am.
Now we have a special segment, the student session. This is a fantastic opportunity to witness the next generation passion and insight into nuclear science. For this student session, we have Asmita MR, research scholar, Department of Physics from CUSAT. We encourage everyone to give our student present your full attention and support.
Good afternoon all. My name is Asmita MR. I am a research scholar from Cochin University of Science and Technology, working under the guidance of Dr. A.K. Rain Kumar. Okay, so in the past 2 days we were discussing about nuclear fission, fusion and sustainable energy and all, right? So now today I would discuss more about the theoretical aspects of nuclear fission and various ways a nucleus splits through the theoretical way. So the title of my talk is Fission Pathways via Funny-Hill's Shape Transition, Shape Parameterization. So in this I would talk about the Funny-Hill's shape parameterization, which gives the parameterization for the shape of the nucleus, which can express a wide variety of nuclear shapes. So after the discovery of fission, it was suggested that the nucleus undergoes fission
as a result of the competition between the Coulomb repulsion between the nucleons, which tries to destruct the nucleus, and the surface tension effect, which tries to stabilize the nucleus. So during this process of fission, the nucleus transfers from the ground state shape to a configuration of two fragmented nucleus. So in this path, the nucleus undergoes various structural transitions in this shape, and which is given by the shape parameterization. So using this shape parameterization, we can generate the potential energy surfaces, which defines the evolution of energy of a nucleus during the process of fission. And to say multidimensional map of the nuclear potential energy in the deformation plane. So from this potential energy surface, we can study various phenomena related to nuclear physics, like the fission barriers, fission dynamics, vibration, motion, and other collective phenomena in nucleus. So coming to Funny-Hill's parameterization, it is expression of the nuclear radial function, which is given by the profile function, as you can see, the rho square, which represents the distance from the surface of nucleus to the axis of symmetry of the nucleus, which is given in terms of a quadratic expression for the parameter b greater than 0. B is related to neck of the nuclear deformed nucleus. So you can see in the image, as nucleus deforms, it forms a dumbbell shape in between, and the neck represents the represents the middle portion, and where the nucleus splits. So when the B is associated with the neck thickness, and when it is less than 0, it undergoes it is moving to fission, and that was given by another expression where an exponential term is added to allow a gradual transition to the splitting of the nucleus. So in order to to choose the right deformation parameters, we have to find a meaningful deformation parameter which can be equated to a physically meaningful property. Like in the case of Funny-Hills, we choose the parameters C, H, and alpha, where C represents elongation, which is derived from the volume conservation condition. As nucleus deforms, its volume remains constant. And then we derive the neck thickness parameter H, and in terms of the parameters A and B. And then we also have the asymmetry parameter, which represent the ratio of the mass of fragmented nucleus. So from this CH and alpha parameters, it is difficult for us to generate a rectangular mesh in which it gives all the wide variety of shapes of the nucleus, but excluding the forbidden shape. Forbidden shapes are where the formula of profile function may give some mathematically possible shapes, but it is not physically meaningful. So in order to, when we need to do further calculations, we have to avoid these forbidden shapes. So in order to do that, we derive the generalized or collective coordinates, that is functions of the shape parameters CH and alpha. These are given by Q1, Q2, Q3 in the case of Funny-Hill's shape parameterization. And after generating these collective coordinates of Funny-Hill's shape parameterization, we use this to calculate the potential energy of the nucleus, various components of potential energy of the nucleus, the surface component, the volume component, and the Coulomb component, etc. So there are there are different models of the potential energy of nucleus. The first one is, as everybody know, the liquid drop model, which gives the Bethe-Weizsäcker formula, or the semi-empirical, which is from the semi-empirical mass formula, which includes only surface, volume, and Coulomb terms. In case of the new models, LSD model, it includes a curvature correction and the congruence correction, where the curvature of nuclear shape, the deformed shape is also taken into account, as well as the discreteness of the nucleons in the nucleus is also taken into account. As you know, liquid drop models seems the nucleus is a continuous fluid, but in general it is not continuous, it is a discrete particles, right? So in order to address these quantum effects, we included the congruous energy as well in the liquid drop model. That gives the LSD model. Another model of nucleus is potential energy is FRL-DM model, which addresses the finite range of nuclear force. As you know, strong nuclear force is short range. The finiteness is also addressed, and the nuclear surface is actually not a sharp boundary, it is actually diffused, and that is also taken into account in the FRL-DM model. So these are functions of in this formula, this B, C, B, S, these are all functionals of various energy terms, like BS is surface term, BC is a Coulomb term, and BJ, BK are rotational components of the nuclear motion. The rotating nucleus is taken into consideration. And similar in the FRL-DM model. And generating the potential energy surfaces of barium 174 nucleus, which is a medium mass nuclei, for which the potential energy surface plays significant role in nuclear fission dynamics, unlike other heavy mass nuclei. So we taken into account the BA nucleus, and the potential energy surface gives a glance into the fission pathways, where the fission pathways are the lowest energy pathways, in which you can see from a local energy minimum to another local energy minimum, the nucleus travels. So the So here we have plotted the potential energy in the Q1, Q2 deformation plane, where Q1 is elongation of the nucleus, and Q2 is the neck thickness of the nucleus. So here you can identify a fission path from Q2 is equal to 0.6 to from Q2 is equal to 1. And for FRL-DM and LSD model. Then this is done for the Q1, Q3 deformation plane, where we need to analyze the asymmetric fission and symmetric fission. In this case, when the nucleus transforms from one lower energy to another lower energy, it undergoes fission, and when the Q3 is the path shown in the image, when Q3 is 0, that is a symmetric fission. Q3 represents the symmetry, and another probable path is asymmetric fission, when Q3 changes and the nucleus transfer from lower energy to another lower energy. So these are identical in case of FRL-DM and LSD, but in the previous slide you could have seen a till difference from the two images, where FRL-DM shows another path which is not completely moving to the lower energy, which can be termed as an artificial path of fission, which is actually not present in for which the nucleus doesn't undergo fission. So that is present in FRL-DM model. Why? Because the FRL-DM doesn't take into account the curvature effect. So when we plotted the LSD model, the path disappeared. That is how the LSD model differs from the FRL-DM model. So that is the work we were carrying out. So from here we can conclude about the feasibility of Funny-Hill's shape parameterization comparing to other parameterizations like Hill-Wheeler or Cassini ovals, which take into account only minimal set of deformation parameters like C, H and alpha, and it can give a large variety of nuclear shapes, which is computationally efficient and accurate. So using this, we have generated potential energy surfaces from which we can calculate the fission pathways and the fission barrier heights. So fission barrier height is represented by the maximum energy of along the fission path, maybe the middle point of the fission path. So it is all about our work, the future work. We can calculate other, this the same for other actinoid nucleuses, and we can try about other nuclear models or potential expressions.
In calculating the potential energy, have you taken the very short range PP, NN, PN interactive forces also? In calculating the potential, have you taken the very short range nuclear forces of PP, PN, NN forces, attractive forces? Has it been considered? Yes. Considered? The potential, you are looking for the potential, and you are looking for the potential and take into consideration the curvature also, which was not considered in the semi-empirical formula earlier, correct? No? In the new model. So in that model, have you taken into consideration the PP, PN and NN short-range attractive forces also?
Yes, the short-range forces are considered, the force between nucleons are considered in terms of the various type of interactions. Like one is Coulomb attraction, attraction and repulsion between the PP, and then surface tension effects, and then the volume energy is considered, then the curvature effect is considered, and similarly different types of potential is calculated, energy is calculated. Anyway, it is barium. But anyway, it was barium nucleus. But
Thank you, Asmita, for those interesting presentation. Asmita to be presented. Now let's take a short tea break. We'll be back in 15 minutes.
Hello, 1 minute. Hello, excuse me.
Yesterday, at attention.
One minute. Excuse me. Student session. There's only one student presentation. So we have got plenty of time. So any one of you are interested to have a close interaction with the BRC scientists, please come. You can talk to them. You can ask any number of questions. We are free to answer. So please come in front. All students, please come in front. Please come. Don't hesitate. Come. It is for you. We have done this for you only. We have done lot of effort. This is not an easy job. Don't think that arranging is an easy job. We have spent a lot of money. We have brought a lot of people, all for you. So please come and interact with the scientists. You can ask in Malayalam, no problem. There are many Malayalis here. K.N.S. Nair is there. Bhaskaran, all are Malayalis. Please come in front. Some of you, please come in front. You can ask some serious doubt. We can have some interaction. It is not asking questions. You can have some interaction. How to get a job from BRC? How to go to BRC for doing projects? What other things are in BRC? What all things you can see? Where is BRC located? What are the different organizations coming under DAE? All things we can explain to you. So please come in front. Come. All of you come. Come. Why are you doubting? See, in life, nothing has to be feared. Everything has to be understood. This is told by Madame Curie. In life, nothing has to be feared. Everything has to be understood. You come in front. Please come. Come. Please come. Come in the front row. Front row. Come to the front row. We have got half an hour time. Come to the front row. All of you come to the front row. അത് ഞാനല്ല, അത് താൻ പറയണം എനിക്ക് because കഴിഞ്ഞിട്ട് പറയാം. Now, this is an opportunity for you. I am telling you, this is a This is a God-given opportunity for you. There are so many internationally known scientists who are assembled here. We have come here to teach you. We have come here to help you. We have come here to know what are the opportunities in BRC. So please utilize this opportunity. Don't waste your time. So ask some question. If you got any doubt, after anything, need not be science. You can ask anything about how to do project, how to get a job in BRC. So you can ask so many things. So ask some question. We are ready. Don't get scared. Don't get scared. Ask some question. Who is the first one? First one. Vishnu, give to them. One by one. First one.
Hello, sir.
Yes.
My question is that how can nuclear physics attract a person outside physics?
Physics. Praveen, just answer. Nuclear.
How can nuclear physics attract a person outside physics? That outcome. No. If a person...
You can go to this NASA where they are doing physics. Or you
That's
can
not
go
my
to,
question.
We can go to
Let me
ISRO
complete.
where they are doing a lot of physics.
If
part of science only. Whether you call it physics, chemistry, maths, biosciences, life sciences or engineering, they all originate from some sort of knowledge base. We call it, we segregate it at physics. So a person outside physics also, he has a knowledge base. Now when you are talking about language, now people have not been able to decipher, say let us say Indus language. Now, what is physics going to do or what is the science going to do to decipher that language? Maybe AI is a solution. Maybe dating is a solution. Maybe the picture, what do you call that, understanding the symmetry, picture, that is another solution. So this is how many of the archaeology students, many of the history students, many of the Sanskrit students, language students, they keep coming, looking at the science, whether it is physics, chemistry or anything, even mathematics.
Actually, radiocarbon dating, radiocarbon dating is sort of physics.
So it is like this, a non-science student, when I even say that a non-physics student, I will put it as a non-science student. There is nothing like science. It is your, the state of mind to know, to understand. So this is what I feel that the what do you call that, the enthusiasm of a non-science student coming to science and look is the quest. We are questioning and then we are exploring. What is it? So it is the knowledge base and your thrust to know the knowledge. This is what I feel.
Okay, thank you. Next question. Next question. Next one.
So, for example, if my father asked me about nuclear physics, how can I express it? How can somebody get interested in nuclear physics without a proper knowledge in physics or something that? Like, my father is a completed just 10, he doesn't know about physics more. How can nuclear physics attract somebody without a proper knowledge?
See, when you come to college, you learn many subjects, physics, chemistry, maths, biology. Somebody like mathematics, somebody like physics. It's only your important qualities. Somebody will like physics. And you might have heard so many physicists, like Erdika Fermi, Homi Baba. So by hearing this, by seeing by knowing their experiment, their work, you will be naturally tempted to some particular field. That makes you attractive. There's no particular reason why somebody should like physics. This is all your important quality.
So we have so many branches in physics, like electronics, nuclear physics.
You like physics, no? You like physics.
Yes.
So you should be. Everything is actually mother of the science is mathematics, father of the science is, you can say, physics. Like that.
My question is, how nuclear physics is different from other branches of physics?
Everything in the world is nuclear. How the sun is burning. In the world, everything is nuclear. Without nuclear, life can't exist. What is happening in the sun? Nuclear fusion. Without sun, can we live? We cannot live. What is the radiation? Radiation coming from sun. Cosmic ray, this ray, that ray. Everything is physics. Without physics, nothing can exist. So this is natural, this thing. Everything, how sun is moving, planets are moving around the sun, how moon is moving around the sun, everything on physics, all physical laws. Physics, how the Newton's apple fell on Newton's head, everything is science. Thank you. Next.
See, dear friend, it's like this. Today you must be reading in newspaper that the temperature is going up. ചൂട് വളരെ കൂടുതലാണ്, യു വി റേഡിയേഷൻസ് കൂടുതലാണ്. ഇപ്പോൾ 10ാം ക്ലാസ്സിൽ പോയിട്ടില്ല നിങ്ങളുടെ ആരെങ്കിലും എങ്കിൽ കൂടി, അല്ലെങ്കിൽ മോസ്റ്റ് ഓഫ് ദ പീപ്പിൾ ഇപ്പോഴും അതേ ന്യൂസ് പേപ്പർ വായിക്കുന്നുണ്ട്. ഇപ്പം ന്യൂസ് പേപ്പർ വായിക്കുമ്പോൾ ഒരു ചെറിയൊരു ക്യൂരിയോസിറ്റി ഉണ്ടാവും, എന്താണ് ഈ യു വി എന്ന്. യു വി ധാരാളം, ഇപ്പോൾ കഴിഞ്ഞ ഒരാഴ്ചയായിട്ട് പേപ്പറിൽ മുഴുവൻ യു വി ആണ്. എന്താണ് യു വി എന്ന് ആരെങ്കിലും ചോദിച്ചു എന്ന് വിചാരിക്കുക. ഫോർ എക്സാമ്പിൾ, അദ്ദേഹത്തിന് അറിയില്ല. അപ്പോൾ യു വി എന്താണെന്ന് ചോദിച്ചു കഴിഞ്ഞാൽ യു ഹാവ് ടു എക്സ്പ്ലെയിൻ ടു ഹിം ദാറ്റ് ഈ ലൈറ്റ് ഇതിൽ വിസിബിൾ സ്പെക്ട്രം ഉണ്ട്, ചിലത് കാണാൻ പറ്റും, ചിലത് കാണാൻ പറ്റില്ല. അപ്പോൾ വിസിബിൾ സ്പെക്ട്രം ഉണ്ട്, വേറെ സ്പെക്ട്രം ഉണ്ട്, അല്ലെങ്കിൽ അതിൽ യു വി സ്പെക്ട്രം ഉണ്ട്. തീൻ്റെ അടുത്ത് പോയിട്ട് ഒരു സ്പൂൺ ചൂടാക്കി കഴിഞ്ഞാൽ അത് റേഡിയേറ്റ് ചെയ്ത് കഴിഞ്ഞിട്ടുള്ള ഇൻഫ്രാറെഡ് സ്പെക്ട്രം ഉണ്ട്. സോ അങ്ങനെ അദ്ദേഹത്തിന് എങ്ങനെയാണ് ഇൻട്രസ്റ്റ് ഉള്ളതെന്ന്, അല്ലെങ്കിൽ ഒരു പക്ഷേ ചോദിക്കാൻ അറിഞ്ഞു എന്ന് വരില്ല. ഒരു 4 ആൻസേഴ്സ് അങ്ങോട്ട് പഠിപ്പിച്ചു കൊടുത്തു കഴിഞ്ഞാൽ ദെൻ 5ാമത്തെ ക്വസ്റ്റ്യൻ ഓട്ടോമാറ്റിക്കലായിട്ട് വരും. ഇപ്പം നിങ്ങൾ ക്വസ്റ്റ്യൻ ചോദിച്ചിട്ട് എനിക്ക് പെട്ടെന്ന് പറയാൻ പറ്റാത്ത പോലെ അദ്ദേഹം നിങ്ങളോട് ചോദിച്ചു കഴിഞ്ഞാൽ നിങ്ങൾക്ക് പറയാൻ പറ്റാതെ ആവും. അതാണ് സയൻസിൽ. സയൻസിൽ ബേസിക്കലി എന്താണെന്ന് വെച്ച് കഴിഞ്ഞാൽ യു നീഡ് ടു build that curiosity and then you need to ask questions and get answers and solutions. ഇപ്പം ഞാനൊരു എക്സാമ്പിൾ പറഞ്ഞു എന്ന് മാത്രമേ ഉള്ളൂ. യു വി അങ്ങനെ ഒരുപാടുണ്ടാവും. ഇപ്പം ഗ്യാസ് കത്തിക്കുകയാണ്. ഇപ്പം രാവിലെ ഭഗത് സിംഗ് പറഞ്ഞു വോൾട്ടേജ് ഒരു സ്പാർക്കാണെന്ന്. ദാറ്റ്സ് എ സയൻസ്. ആൻഡ് ന്യൂക്ലിയർ ഫിസിക്സ് ഓർ അറ്റോമിക് ഫിസിക്സ് ഓർ കെമിക്കൽ ഫിസിക്സ് ഓർ മെഡിക്കൽ ഫിസിക്സ് കൺസിഡർ ചെയ്ത് കഴിഞ്ഞാൽ എവറിത്തിങ് ഈസ് സെയിം. ഇറ്റ് ഈസ് എ നോളജ് ബേസ്. സോ വി സെഗ്രിഗേറ്റ്. എനിക്ക് കുറേ കാലം മുൻപേ എൻ്റെ ഒരു റിലേറ്റീവ് ഉണ്ടായിരുന്നു. അദ്ദേഹം ഒന്നും പഠിച്ചിട്ടുണ്ടായിരുന്നില്ല. ഒരു ചെസ് മാസ്റ്ററായിരുന്നു. മാത്തമാറ്റിക്സ് ഒന്നും പഠിച്ചിരുന്നില്ല. ഞാൻ പഠിക്കുന്ന കാലത്ത് അദ്ദേഹത്തിൻ്റെ അടുത്ത് പോയി കഴിഞ്ഞാൽ ആകെയുള്ള വിദ്യ, അദ്ദേഹം അടുത്ത് വരും, വേറെ ഒരു പണി എനിക്ക് ആരും സമ്മതിക്കില്ല, മാത്സ് ഡിസ്കസ് ചെയ്യും. അദ്ദേഹത്തിന് എന്താണെന്ന് വെച്ച് കഴിഞ്ഞാൽ ലീലാവതി പഠിച്ചിട്ടുണ്ട്, ലീലാവതിയിലെ ഒരുപാട് പഠിച്ചിട്ടുണ്ട്. അപ്പോൾ നമ്മളുടെ പുതിയ മാത്തമാറ്റിക്സ് സിസ്റ്റമായിട്ട് തീരെ ഫെമിലിയർ അല്ല. ആ ഫെമിലിയാരിറ്റി ഞാൻ ലിങ്ക് ചെയ്ത് കൊടുക്കുമായിരുന്നു. അതെങ്ങനെയാണ് ലിങ്ക് ചെയ്യേണ്ടത്, എങ്ങനെയാണെന്നത് പെട്ടെന്ന് ഔട്ട്റൈറ്റ് ആയിട്ട് പറയാൻ പറ്റിയെന്ന് വരില്ല. ബട്ട് ദാറ്റ് ഈസ് ഹൗ യു ഹാവ് ടു ബിൽഡ് ദാറ്റ് സയൻറ്റിഫിക് ടെമ്പർ amongst the people.
Next one, some girl. Come on, ask question.
Sir, my question is, how can we prevent the use of nuclear energy for weapons development by keeping in the basic uses of nuclear energy? It is useful to us, but also how can we prevent the misuse of nuclear energy for weapon development?
It is mainly IAEA, this International Atomic Energy Agency. They are supposed to look after every nuclear labs, what they are doing, what is the purpose. If they are mainly all the nuclear labs working all over the world, they are mainly used for making fuel for nuclear reactors. There are some countries who develop weapons, but that you have to declare to IAEA. Tell me how many weapons?
Thank you, sir.
Yeah, he really wants it.
Sir, that is my only basis. People won't think like me, everyone. That is why, we can see.
I'll answer your question. So what makes you think that we should not develop nuclear weapon? First, to think about yourself.
Sir, day before yesterday, I have read a news that 400 children died in Gaza. So that made me think. Not by nuclear weapon. But these kinds of things happen now because of nuclear energy. And after reading that news, I came to this symposium. So Just strike in my mind.
Nagasaki, afterwards.
No, nothing is there connection.
I just want to tell you one thing. I just want to find out, just see, if you know Atal Bihari Vajpayee, our former Prime Minister, okay, he made a statement. India has to develop nuclear weapon not to fight. Somebody instigating you.
Maybe,
okay, somebody among you who is instigating fight means he is finding you weak. Let me instigate her. The moment you start retaliate, he will again retaliate with higher thing. It is like that India wants to prevent his neighboring countries or whoever countries to instigate them. Once India becomes powerful in every aspect, nobody will fight with India, so there will be no loss in life, no war will be there. Okay, so development of nuclear weapon has to be supported, this just because to deter other people to fight against us, so that we can focus on other better things.
Yes, since every coin has two sides. you
So
can
that
say
is
like
why it is very important
One more
to
thing.
become strong.
One more thing
Yes.
I want to add. After 1945, after Japanese dropping of bombs in Japan, there Russia started making bombs. America had 10,000, Russia had 10,000, 20,000. But they didn't bother to fight each other because they were afraid. So it is a sort of, the nuclear weapon prevented a further war. There was no third world war because they had enough weapons to kill each other. Mutually assured this thing. So it is a sort of thing that other fellow is afraid that he will come and bomb you. He is afraid that other fellow will come and bomb you. So it's a sort of, stoppage of war. Deterrence. Okay? Next one. One minute. അടുത്ത question.
See, to answer your question, just 2 points I want to tell. One is that there is arms control treaty between various countries in the world regarding the weapons and use of weapons, number one. And if more countries come into safety and they start thinking more and more treaty can come, it can get reduced, number one. Number two, there is some countries have themselves declared that no more weapons are being developed even though we have the material. Number three is that the material required for making nuclear weapons will be enriched uranium or plutonium, which are highly fissile material. Those materials all over the world, in any country for that matter, is under the safe control of the country, and many of them are not only under the country's control, but under the control of the IAEA, safeguard, inspection, and all those things are there. Even if I move 1 gram of plutonium from here to here, somebody else will come to know. There are controls built in for these purposes. So these are the things which makes us feel safe, even though we have weapons in the custody of many people.
Next question. We don't have much
Sir,
time.
how can I get a project at BARC?
You can get a job in BRC.
Project work. It's project.
Recently I helped, I am happy to inform you. 2 students from St. Thomas College, they came to our Vijnan Sagar, but I used to go there. They wanted to go to BRC. So I talked to BRC people. I had some contact there. So he told me there are you go to BRC website, HRD website. There are some forms are there. You fill up the form, get it signed from your department, you send it. You have to say that there are some column in that. You have to fill it properly, you send it, most probably you will get it. There are some condition for that. Then you should be either you should not be in the first semester or in the last semester. You should be either you should be in second, third or fourth.
Sir,
you are not allowed to, you will not get it if you are in first semester.
Sir,
or in the last semester. He can tell you better than
to make life simpler, all you have to do is you have to address a letter from your principal to head Human Resource Development Division of BARC. The Human Resource Development Division will write back to you stating whether your application has been met or not. So only a letter from your principal, and as sir told, it has to be a person from at least the third year
there's
of your
one form is there that you have to fill it up. So recently it happened and they got it also. These 2 girls from St. Thomas College got it for 3 months.
The project is.
And nowadays it is very easy. They allow more people. After this this thing, it is very easy to go to BRC. Next question, next. Hi. No, Avil. Use it. You're a student. Let the
Sir,
college know.
I don't want to sound political. I don't want to sound political, but why does Kerala doesn't have a nuclear power station and irradiation center
Very interesting
or
question.
a rare earth
Very
extraction
interesting.
center?
That's why we are struggling. We came here to have awareness. What happened?
I don't know. Is it cost related or anything else? I don't know.
Nothing like that. One day.
Is it because of the lack of information?
See, there are two things. One is Kerala is highly populated. There are not much free areas. Nuclear reactor, you need some free areas. Kerala is highly populated. Second reason is Kerala people are afraid because of the bad information they have been given. They are given a lot of misinformation. Nuclear reactor is not a bomb. Nuclear reactor can never explode. People think that nuclear reactor means it can explode, it will release a lot of radiation, it will damage the people. A nuclear reactor never explodes. There is a lot of... Kudangalam is standing very near to you, at the mouth of Kerala. At the mouth of Kerala. At the mouth of Kerala, you have a nuclear reactor. A nuclear reactor in Kerala, in Kudangalam reactor, you are buying power from there to here. How it is possible? You can use their power, but you can't have a reactor in Kerala. So these are very old. Yeah, especially this so-called Kerala Shastra Sahitya Parishad. There are so many retired BSc, disgruntled people. They nuclear. Ramagundam. They are buying from there, Ramagundam and all. And these transmission laws now. Yeah. I know,
I'm going to leave, so I'll ask soon and I'll go. My question is actually to you, Mr. Bhaskar, because I want to ask, why does India only use heavy water? There are many other more efficient coolers like liquid sodium, then helium, then and molten salt coolers. There are several others. Why does India use heavy water? You said that heavy water manufacturing is a very energy intensive and complex task. So why don't we rely on liquid sodium or things like that?
See, Indian nuclear power program is, the first phase is based on natural uranium. We don't have any uranium enrichment, and the resources of uranium is limited in the country. So we have taken a decision that our first phase will be what we call as pressurized heavy water reactors, what we call as PHWRs. Now all the reactors other than Kudankulam, all are PSWRs today. Now the question is like this, when you are having natural uranium, you need to have heavy water as the moderator, because the number of neutrons per fission what you get is limited. So to sustain the thing, you should not reduce the number of neutrons available for further fission. So heavy water doesn't absorb neutrons, and it will do that. If you want to operate naturally, without heavy water, then you need certain level of enrichment. Enrichment means the amount of uranium-235 in the fuel you should increase. This technology also is equally energy efficient, or more than probably heavy water production. They are energy efficient technology. So that is why we have not gone for, or we have selected heavy water, natural uranium as the system for the first phase of reactors. Now, as you said, sodium is only a coolant. Liquid sodium is a coolant. It cannot do a reactor by itself. If you want to do that particular thing, it has to be a fast reactor, what we call as fast reactor. And fast reactor need cooling medium. Fast reactor, you have plenty of neutrons, more fissile material than natural uranium. So you can afford to have, there is no moderator there. So that you can have. And manipulating this, you can slightly produce further fuel also using these fast neutrons. That is a different technology altogether, which we are going to commission at Kalpakkam. There is a fast reactor program. That is what people call as thorium will be converted to uranium, and then uranium will be further used as a fuel, which will again produce some uranium to thorium to uranium. That sort of cycle goes. So your question will be, why heavy water? Heavy water with natural uranium, overall energy requirement is less compared to enriched uranium with the other type of technology. All the other what reactor we had at Tarapur long before, they were enriched uranium with light water reactors. It was not using heavy water.
Hello. Next question is from this side. Will stop. Hey, don't go, please. We have to give one gift to you on behalf of our book. Because he asked a lot of questions. He's a student. He's not from a given college. You. Sir, next question from this side. We don't have time. Only 10 more minutes. Then we'll stop it. Mic kodu. Vishnu.
Sir, I did not have a particular
You
question.
tell me your name first, then introduce.
I am Nangema. I didn't have a particular question. I just wanted to offer my perspective on the debate about why Kerala didn't have a nuclear power plant.
Yeah.
I don't think we can say Kerala has more unscientific people. I just think we hear more from the unscientific people of Kerala.
No. Japan is a country where a lot of people, there may be population density Japan
No,
will be much.
I just meant that other states also have unscientific people, but we just hear more from the unscientific people in Kerala because we have a culture of protest. We are more likely to protest when something happens.
We are argumentative. Actually, people are not understood properly what is good for Kerala. People are just simply telling that, see, you heard about Kudankulam, this Mullaperiyar Dam. Mullaperiyar Dam will break. It is not going to break. It's all scientifically done. So it is all these bad things, all these things are causing all the problems. See, we should have scientific temper. The scientific temper is not there. That's the problem.
കേരളത്തിലെ പൊതുവെ ജനങ്ങൾക്ക് റേഡിയേഷൻ എന്ന് കേട്ടാൽ ഒരു പേടിയുണ്ട്. അത് ഈ റേഡിയേഷനെ പറ്റി ശരിയായൊരു പെർസ്പെക്റ്റീവ് ഇല്ലാത്തതുകൊണ്ടാണ്. ഒരു കാര്യം മനസ്സിലാക്കേണ്ടത്, വെദർ ന്യൂക്ലിയർ എനർജി ഈസ് ദർ, ന്യൂക്ലിയർ പവർ വന്നാലും ഇല്ലെങ്കിലും നമ്മളെല്ലാവരും ജീവിക്കുന്നത് ഇൻ എ സീ ഓഫ് റേഡിയേഷൻ. നാം ശ്വസിക്കുന്ന വായു, നാം കുടിക്കുന്ന വെള്ളം, കഴിക്കുന്ന ഭക്ഷണം, ഈവൻ നമ്മുടെ ബോഡിയിൽ പൊട്ടാഷ്യം ഉണ്ടല്ലോ, പൊട്ടാഷ്യം എസെൻഷ്യൽ എലിമെൻ്റാണ്. അതിൽ 0.12% K40 റേഡിയോ ആക്റ്റീവാണ്. അങ്ങനെ നോക്കിക്കഴിഞ്ഞാൽ നമ്മളെല്ലാവരും ഒരു റേഡിയോ ആക്റ്റീവ് സോഴ്സാണ്. നമുക്ക് റേഡിയേഷൻ ഇല്ലാതെ ജീവിക്കാൻ പറ്റില്ല. റേഡിയേഷൻ കമ്മിങ് ഫ്രം ഔട്ടർ സ്പേസ്. നമ്മുടെ ചുറ്റും നമ്മളിരിക്കുന്ന ഈ ബിൽഡിങ്ങിലും യുറേനിയം, തോറിയം എല്ലാം ഉണ്ട്. അതിൽ നിന്ന് നമുക്ക് റേഡിയേഷൻ കണ്ടിന്യൂസ് ആയിട്ട് കിട്ടിക്കൊണ്ടിരിക്കുന്നുണ്ട്. അപ്പോൾ നമ്മുടെ ചുറ്റും റേഡിയേഷൻ ഉണ്ട്. നമുക്കൊരു കൊല്ലത്തിലെ ആകെ ലഭിക്കുന്ന റേഡിയേഷനിൽ 85% ഈ നാച്ചുറൽ റേഡിയേഷനിൽ നിന്നാണ് കിട്ടുന്നത്. ബാക്കി 15%, 10%-ലധികം മെഡിക്കൽ ട്രീറ്റ്മെൻറ്റ് ആൻഡ് ഡയഗ്നോസിസ്. ഈ ന്യൂക്ലിയർ റേഡിയേഷൻ, ന്യൂക്ലിയർ റിയാക്ടറുകളുടെ ഭാഗത്ത് ജനങ്ങൾക്ക് കിട്ടുന്ന റേഡിയേഷൻ വെരി സ്മോൾ പെർസെൻറ്റേജ്, ലെസ് ദാൻ 1% ഓഫ് ദി അലൗഡ് ലിമിറ്റ് ബൈ അറ്റോമിക് എനർജി റെഗുലേറ്ററി ബോർഡ്. അപ്പോൾ ഈ ഭയം ഇല്ലാതാകണം ആദ്യം തന്നെ. എന്നാൽ തന്നെ
Sir, I did not mean that I am afraid of nuclear power. I meant, I just suggested a reason.
Not you. It is a general perception. Generalized പറഞ്ഞാണ്.
Why you are afraid? We are come here to allay your fears. നിങ്ങൾ ഈ പൈസ ഒക്കെ സ്പെൻഡ് ചെയ്തിട്ട് വന്നെന്തിനാ? നിങ്ങളുടെ ഫിയർ മാറ്റാൻ, റേഡിയോഫോബിയ മാറ്റണം. റേഡിയേഷൻ ഈസ് നോട്ട് അറ്റ് ഓൾ ടു ബി അഫ്രൈഡ്. ഇറ്റ് വിൽ ബി അഫ്രൈഡ് ഇഫ് യു ആർ ഡൂയിങ് സം അൺകൺട്രോളബിൾ തിങ്സ്. Otherwise, radiation is not at all be fear. Radiation is everywhere, as he told. Your wall contains radiation. It contains thorium, uranium, small amounts. Air contains radon. Radiation is everywhere. In the sun, cosmic rays, what protons. So radiation is everywhere. You need not be afraid. But if you are getting radiation beyond some levels, then you will use it.
See, forget about the nuclear energy. You remember some few years back, there was a drive for installing computers in all the offices and automation. What happened? Was there any resistance? Was there? Why? People are afraid they will lose the job. That was their understanding. But now you see, anybody is there without a computer or a smartphone. Things are going smoothly. So there is a resistance for everything in Kerala. That is the basic thing. Thank you.
Actually, I used to be pretty indifferent about the entire concept of nuclear energy, and in October we visited Kudankulam.
Do one thing. If you got any further doubt, you can interact with us. Now we don't have. Talk.
Yeah, we visited Kudankulam from our college, and it kind of changed, I think we can say, our entire perspective about the safety measures. Yeah.
You are positive about nuclear?
Yeah.
Yeah, very good. Give me a big hand. That's what we wanted. We came here to have a positive impact on you. We came here all the way to have a positive impact on you. Without positive impact, no, we have spent a lot of money for this. We have brought so many people from BRC. This is done because to have a positive impact on you. Nuclear is not bad. It's not a devil or it's not a ghost. Nothing to be feared. Nothing else to be feared. We are here to help you.
No, it is a very positive thing that you said that you are not afraid of nuclear energy. So, if we are not afraid of nuclear energy, it is our duty to spread the information around that there is nothing to be afraid of.
I have worked 40 years in nuclear energy, 40 years. Not only me, myself, all people. I have handled plutonium. I'm not joking. I handle plutonium. KNS Nair may be knowing. It is the most dangerous element man has ever discovered. You have to work carefully. Nothing happened to me. My hands are all right. My eyes are all right. Everything is okay. I'm perfectly okay. So what happened? Nothing to be feared. It's just simply people are mad. No, nuclear means you have to handle everything carefully. Nothing to be worried. Thank you. Next question.
Sir, it's not a question. I am Dr. Ambli. I'm head of the Department of Economics.
Tell me.
So I don't know anything about science. We stopped studying science at the 10th standard. After that, we are into social science.
Yeah.
So as a layman view,
Yeah.
this throughout the sessions we were here,
Yeah.
but we couldn't understand anything. Sorry to say,
You didn't
because
understand?
we don't know.
You could ask,
the science,
ask
right?
the speakers at that
so,
time.
as a layman,
Okay.
we are afraid of nuclear energy.
But what is the reason?
As you said, the radiation. We always
We-
talk
we are
about
getting-
radiation.
Madam,
and
we are
all those
getting
things,
radiation
right,
from
sir?
everywhere. Everywhere.
Yes, we
See,
are
sun,
living-
what is sun rays? Radiation,
Yes.
electromagnetic
Yes.
radiation. See,
So
when
what-
you see radiation, you don't be afraid. Radiation is everywhere. Radiation is not a thing to be afraid. Radiation beyond some level, beyond some intensity, you have to be afraid.
So, sir, I have a humble suggestion. If we can start from the rural area, teach them, or this information should be spread to the rural area.
That is a good idea.
Throughout the, see, it should start from the school itself.
Yeah, that is we are trying. What happened is
Even if now with, we have this rainy season coming up and we will have thunder, and while using mobile phone, it's very easy to get a shock. All these
Yeah.
things are going through in the WhatsApp university.
Yeah.
So those people who are from the rural area and they are access to WhatsApp, they spread this, especially after the age of 50. We love our life, no, more than the young age. So we are prone to all these information and we are ready to accept. See, as you said, Mullaperiyar is not going to break.
Yeah.
We know, but every time when the rainy season comes, the monsoon comes, then this propaganda will start. So the people, common people
See,
from the rural area,
yesterday somebody made a comment by going by flight is dangerous. Some people are afraid to go by flight.
yes.
Because flight is the most safest journey, they say, as per the science. Flight is the most safest
Statistics
journey.
shows. Yes,
So
sir.
this is like that now. There's some basic for that.
So the
There is no
educated
scientific
folk, especially from the science background, they can understand and they can. So as a social scientist, what I feel is we have to start from the school. We have to have some policies for the rural people through Grama Panchayat.
That part I agree. We
So
have to go to school, but we don't have the resources to go to school. We are such a small
So
organization.
we can submit a proposal as a
You
social
call us,
scientist. We can
you call us,
propose.
we can come to any, we can go to
So
any
we can-
school or any people we can talk. Whatever we know, we can teach them.
മാഡം അടുക്കള കയറാറുണ്ടോ അടുക്കള കയറാറുണ്ടോ
Of course, sir. Every day I
ആ
cook for
തീയുണ്ടോ
myself.
അവിടെ
എന്താ sir?
തീയില്ലേ അവിടെ
ഉവ്വ്
ഗ്യാസ്
ഉവ്വ്. ഇന്ന് രാവിലത്തെ ഒരു സെഷനില് ഗ്യാസ് ലൈറ്റർ എങ്ങനെയാ ഒരു സാർ ക്വസ്റ്റ്യൻ
Exactly,
ചോദിച്ചിരുന്നു.
exactly.
അപ്പൊ എന്റെ കൊലീഗാണ് പറഞ്ഞത് പുഷ് ചെയ്താലാണ്, കാരണം നമ്മളിത് ഭയങ്കരമായിട്ട് യൂസ് ചെയ്യണതാണല്ലോ sir.
അതെ അതെ അപ്പൊ ആ തീയെ നമ്മുടെ മേല് കത്തി പിടിച്ചാലോ
ആ,
അപ്പൊ എങ്ങനെയാ അപ്പൊ അടുക്കള പോവാൻ
അത്
പാടില്ല
എന്റെ കസിൻ ഇന്നലെ പറഞ്ഞു, ഞാൻ കുക്ക് ചെയ്തോണ്ടിരിക്കുമ്പോ ഫോൺ വന്നപ്പോ പറഞ്ഞു, മോളെ അത് മാറ്റി വെക്ക്, ഫോണിൽ സംസാരിക്കാൻ പാടില്ല കുക്ക് ചെയ്യുമ്പോ. എന്റെ അച്ഛന്റെ സിസ്റ്റർ പറഞ്ഞതാണ്. ഷീസ് ഇൻ കാനഡ. Oh, you are cooking? You move away from...
No, ma'am, just 1 second.
Yes, sir.
Govindan Kuti is having a Vignan Sagar at Ramavarmapuram.
Okay.
You send your student
It is
there.
a scientific
Institute.
experimentation, means I will not say experimentation center, it is a scientific learning center. And if you have some students or some school children in mind, I suggest that you
I can sponsor
I'll get
it.
your number,
you-
sir, of course, because my husband is working in a school. That's in a rural
this is what
area,
I'm
so we
telling.
can collaborate.
If some 10 students, if they can go and visit that Vignan center,
Yes, sir.
they get a little bit idea about some sort of thing. Why a gas lighter works, why a gas cooker works, why such and such material is hotter or not hot, that sort of scientific temper. You can, as a first thing, you can go, means you can tell your husband, pick some 3-4 students, go on a visit to the Vignan Center, have a look at it, and then come. And another thing is that if you have something like that, we are ready for a pilot project.
Thank
Let
you,
us
sir.
see.
Thank you.
Some
And
schools
you
we can
can-
come and then speak to the students.
I'm
School
telling you all.
students, right from primary, secondary. Let us build this particular perspective.
I'm telling all the students, you can contact us. Our
Hey, you
email,
need
our
not-
phone,
you need
telephone
not
numbers are
pick,
available.
Science students, please pick.
Yes, those who are
students.
interested, yes, sir.
If you want, we can form a WhatsApp group.
Of course.
We can discuss your point with us. We'll form
Yes,
WhatsApp group. If you got any doubt, you send a WhatsApp message. We will discuss and give you the answers. No problem. We are there. We are come here to help you. We want to remove all your fears. We want to remove all your doubt, whatever we know. So please cooperate with us. And as Madam told, you can send your students to Vijnan Sagar. There we have got 100 experiments.
Yes.
We have got 2 pavilions, ISR pavilion, space pavilion. How people are going to space, what is the principle of sending a rocket, everything is explained there. So you can bring them. If they don't have money, I will pay for them. No
Thank
problem.
you, sir.
That's all.
There is a model of a reactor also over there.
There's a nuclear reactor they are working. I think now time is getting over. It's 4:30. We have to stop now. I am very much thankful to you. At least some of you asked some questions. We have come here to make you understand what is nuclear power, what are these advantages, why people are. These all things we have to remove your fears. So thank you very much. You can further contact us. Our email, our WhatsApp number are all available with Vishnu, Dr. Vishnu. You can form a WhatsApp group. So you can send us messages. We can reply to you. Okay, thank you very much. Have a good day. Bye. One more minute. Professor Subramaniam is from ISRO. He want to talk to you for 2 minutes.
Good evening. I will not spend too much time. It is a very interesting discussion. We can talk a lot about each and every point that has come as a question. A lot of things to be debated. Very interesting. Yeah. Okay, but I am going to digress a lot because as he correctly told, I am from a different organization. I am from Indian Space Research ISRO. Actually, from the institute, Professor Sarabhai has started in 1947. It is called Physical Research Laboratory, Ahmedabad. So I asked for 1 or 2 minutes just to introduce what ISRO is, what is its mandate, and there are like DAE, Department of Atomic Energy. You heard 2 days, a lot of deliberations on their activities, opportunities. In 1 or 2 minutes, let me try to tell you what are the opportunities in space science. As you know, space is an emerging technology now, very much emerging technology, planetary explorations and payload developments and study of extraterrestrial intelligence. It is very wide open. The explorations have just started. Well, I cannot say just started since the time of Voyager, 1970. This quest is on. So ISRO, especially PRL, offers a lot of possibilities or a lot of opportunities for you to enter into this domain. It is equally challenging domain. So you should be aware of that. Please look the websites of ISRO and PRL. PRL means Physical Research Laboratory, PRL. You can Google search it. Try to be acquainted with this activity. And if you have anything to know about it in more detail, I will leave my phone number here. You can contact me. I live nearby here, near Trichur only. I am available at any short notice call also. I can come and discuss with you. You can actually form small groups, interaction teams, etc. Okay. So this is what I want. The time is very short. I cannot. You know, I am also not prepared how to address you properly. So let me stop it here. Be aware of such an opportunity also, and try to explore in that direction. Whoever is interested in that direction, we are there to help you. Thank you very much.
Now we have 10 minutes break, tea break. After 10 minutes, we are going to come back here. 10 minutes break. Then the last session, validatory function, last session. So 10 minutes break.
Attention please. A watch has been received from here, and if its owner comes here, the watch will be returned.
improve the golden moment of opportunity and catch the good that's in our reach is the great art of life. Good evening, everyone. It's the time to begin the valedictory ceremony. Now, I request Dr. Rajesh K.R., Dr. Vijay P.S., Dr. Bhaskaran M., Dr. T.S. Muralidharan, Sri Rajesh Kumarji, Dr. K.V. Das to grace the dais. We request all the dignitaries, Dr. Rajesh K.R., Dr. Vijay P.S., Dr. Bhaskaran M., Dr. T.S. Muralidharan, Sri Rajesh Kumarji, Dr. K.V. Das to grace the dais.
Now, it's my pleasure to invite Dr. Rajesh Kea, Head of Physics Department, to deliver the welcome address. Sir, please.
Hello. Respected Principal, Vijay sir, Bhaskar sir, T.S. Muralidharan sir, Rajesh Kumar ji, Dr. K.V. Das, dear faculties, dear distinguished scientists, and dear students of our college and other colleges, good afternoon to all. So this is the conclusion ceremony of the two-day national seminar or symposium on NEST, that is Nuclear Energy for a Sustainable Tomorrow, NEST 25, organized by the PG Department of Physics, Sree Krishna College, Guruvayur, in association with the EIRA, that is Atomic Energy Retirees Association, and INS, Indian Nuclear Society, Kerala. So the aim of this symposium was to provide an overview of India's current nuclear programs and its application across various technological fields. And I am sure that this program has given considerable insights and a deep awareness and has generated interest about the nuclear physics among our students and the public. Let me move to my duty, entrusted with me. The chair of this program is the principal of Sree Krishna College. With great pleasure, I warmly welcome Dr. Vijay sir on behalf of the Department of Physics and Local Organizing Committee. And I'm delighted to take this opportunity to welcome our chief guest, Dr. Bhaskar sir, former CEO HWB. So on behalf of the Department of Physics and the Local Organizing Committee, I welcome Bhaskar sir to this program. The main thrust force behind this program is EIRA and INS. Dr. T.S. Muralidharan, Member, Awareness Committee, EIRA, and Dr. K.V. Das, Vice President, EIRA, is here. So on behalf of our Department of Physics and Local Organizing Committee, I extend a warm welcome to Muralidharan sir and Das sir. And we have our PTA Vice President, Sri Rajesh Kumar ji, is not present here right now. So finally, I would like to extend a gracious welcome to all the members of INS, EIRA, and distinguished scientists present here, and their family members, teaching and non-teaching staffs, students from Sree Krishna College and other colleges. We hope all of you enjoyed the program, and this turns out to be a great success and a memorable one for all of us. Thank you.
Thank you, sir, for those warm and welcoming words. Now I request the esteemed principal of Sree Krishna College, Dr. Vijay P.S., to deliver the presidential address. Sir, please.
എല്ലാവർക്കും നമസ്കാരം. വേദിയിലിരിക്കുന്ന വിശിഷ്ട വ്യക്തികളെ, സദസ്സിലിരിക്കുന്ന വിശിഷ്ട വ്യക്തികളെ, എല്ലാവർക്കും നമസ്കാരം. 2 ദിവസമായിട്ട് നമ്മുടെ ശ്രീ കൃഷ്ണ കോളേജിൽ നമ്മുടെ ബാർക്കുമായി ബന്ധപ്പെട്ട് ശ്രീ കൃഷ്ണ കോളേജും അതുപോലെ തന്നെ ആറ്റോമിക് എനർജി റിട്ടയേഴ്സ് അസോസിയേഷനും ചേർന്ന് നടത്തിയുള്ള പ്രോഗ്രാം ഇതിനെ സമാപ്തിയിലെത്തിയിരിക്കുകയാണ്. ഇതിൽ നിന്നും എനിക്ക് കിട്ടിയിട്ടുള്ള നേട്ടം തീർച്ചയായിട്ടും ഇവിടെ വന്നിട്ടുള്ള വളരെ എമിനൻ്റായിട്ടുള്ള വ്യക്തിത്വങ്ങളുമായിട്ട് കൂടിച്ചേർന്ന് അവരുമായി ഒരുമിച്ചിരുന്ന സമയത്ത് എനിക്ക് കിട്ടിയിട്ടുള്ള നേട്ടം ഒന്ന് മാത്രമാണ്. അത് ഹൗ ടു തിങ്ക്, ഹൗ ടു ടോക്ക്, ഹൗ ടു ബിഹേവ് ഇൻ എൻ അക്കാദമിക് സൊസൈറ്റി എന്നുള്ള വലിയൊരു അനുഭവമാണ് എനിക്ക് ഏറ്റവും ആദരണീയരായ ഇവിടെയുള്ള എത്തിച്ചേർന്നിട്ടുള്ള ഇവിടുത്തെ വ്യക്തിത്വങ്ങളെന്ന് കിട്ടിയുള്ളൂ. അതിന് തീർച്ചയായിട്ടും അവരുള്ള നന്ദി ഞാൻ പറയുകയാണ്. ഞാൻ ദീർഘിപ്പിക്കുന്നില്ല. നമ്മൾ കൂടുതൽ സമയം താമസിച്ചാണ് നടന്നുകൊണ്ടിരിക്കുന്നത്. എന്തുതന്നെയാലും ഇവിടെ എത്തിച്ചേർന്നിട്ടുള്ള എല്ലാ വിദ്യാർത്ഥികൾക്കും റിസർച്ച് സ്കോളേഴ്സിനെല്ലാം തന്നെ ഇതൊരു അനുഭവമായി തന്നെ മാറിയിട്ടുണ്ട് എന്ന് ഞാൻ വിചാരിക്കുന്നു. ഇതിൽ നമ്മുടെ വിജയം ഇന്നിവിടെ എത്തിച്ചേർന്നുള്ള ഓരോ വ്യക്തിത്വങ്ങളുമായി ഭാവിയിൽ നിങ്ങൾ ഓരോരുത്തരും ഏത് രീതിയിൽ അവരെ ഉപയോഗിക്കുന്നു എന്നതിലാണ്. ബാർക്ക് എന്നുള്ളൊരു വലിയൊരു ഒരു പ്രസ്ഥാനത്തിലേക്ക്, ആ പ്രസ്ഥാനത്തിൻ്റെ ഓരോ ഡിവിഷനിലും നമ്മുടെ വിദ്യാർത്ഥികൾക്ക് എത്തിപ്പെടാൻ പറ്റണം. അവരുമായി അസോസിയേറ്റ് ചെയ്തിട്ട് നിങ്ങൾ ഇൻറ്റേൺഷിപ്പുകളോ അല്ലെങ്കിൽ പ്രൊജക്റ്റുകളോ റിസർച്ചുകളോ എന്തിനേറെ അവിടുത്തെ ഒരു എംപ്ലോയി ആയി മാറും എന്നുള്ളൊരു ഡിസിഷൻ ഇവിടെ വന്ന ഓരോ വിദ്യാർത്ഥികളും ഏറ്റെടുക്കണമെന്ന് അഭ്യർത്ഥിച്ചുകൊണ്ട് നിർത്തുന്നു. നന്ദി, നമസ്കാരം.
Thank you, sir, for your words. We are greatly honored to have with us today as our chief guest, Dr. Bhaskaran M., former Chief Executive Officer, Heavy Water Board. Sir, your presence leads immense prestige to this occasion. We cordially invite you to address this gathering.
Good afternoon, friends. The last 2 days, we had a really great session, and I am really amazed with the enthusiasm what students have shown, and in understanding and realizing the goals of this conference. And it was very clear in the final session when quite a good number of questions cropped up, and maybe we may not be able to answer all the questions in one go, but it is a continuous process. And then we are from AERA side and INS side, we are definitely will be with you. And whatever questions, whatever help, whatever doubts are there, we are there to clear from you. And I am really proud that Sree Krishna College do have a great number of alumni with Department of Atomic Energy. Praveen is there. There are other friends also. And probably they are all very near, and then you can specifically help you out. And I feel if that is the goal of the conference, and that indeed is the goal of the conference, and I think it is a great thing. I am thanking all of you, and please keep this spirit, and be there with Department of Atomic Energy, and be with the scientific temple. Thank you.
Thank you, sir, for your insightful address, for gracing your presence. Now we have releasing of digital form of abstract of NEST 2025 by our chief guest, Dr. Bhaskaran M., former Chief Executive Officer, Heavy Water Board. Now, the most anticipated moment of the ceremony, the distribution of participation certificate. We request our chief guest, Dr. Bhaskaran M., to kindly do the honors and present the certificates to the participants. First, Asmita MR, Research Scholar, CUSAT. She had presented a paper presentation.
Next, Advait M. SN Natiga. Archana CN SN Natiga. Akshara R SN Natiga. Anjana TB SN Natiga. Aisha S. Kerala Varma College. Srijita Sridhar VP Kerala Varma College. Jagan NJ Kerala Varma College. Anakha E. Phasi Kerala Varma College. Anashwara Ashokan, alumni Sree Krishna College, Guruvayur. Shivani OS, SN Natiga. Malavika AS, SN Natiga. Devika KV, SN Natiga. Sajna PM, Sri Vyasa NSS College, Vadakanjeri. Adira KM, Sri Vyasa NSS College, Vadakanjeri. Lakshmi KN, Shruti P, Aishwarya G, Shifa Sharin KM, Sri Lakshmi Unni, Abhijit S, Surumi Assis M, Sayan CS. All are from Sri Vyasa NSS College, Vadakanjeri.
Nangemekutti S. St. Aloysius Elathuruthu. Adil Krishna VT, University of Calicut. Anne Chako Panikal, University of Calicut. Adira P, MPMM SN College, Shornur. Deepthi B, MPMM SN College, Shornur. Hiba Nasreen, MPMM SN College, Shornur. Unnikrishnan MS, Faculty, Sri Vyasa. Rahul E, PhD Scholar, Sree Krishna College. Certificates for participants from Sree Krishna College will be given from the department later. Now, to provide us with a concise summary of the symposium, I would like to invite Dr. T.S. Muralidharan, Member Awareness Committee, ERA. Sir, please.
Good afternoon, friends, particularly young friends. All is well that ends well. We have come to the conclusion of an important event, which for various reasons, a combination of reasons, we think that has been conducted and concluded in a very positive sense. We are very happy about it as the association is concerned. I am asked to sum up the deliberations of the last 2 days. അത് അത്ര ആവശ്യമുണ്ടെന്ന് എനിക്ക് തോന്നുന്നില്ല for 2 reasons. One, all of you have listened to the speakers right from the horse's mouth. Number 2, I know all of you are quite eager to pack up and go home. But then, still, I would like to make a very brief presentation, extremely brief presentation, primarily for the purpose of putting it in an encapsulated manner in a certain perspective. I am not going to cite all the speeches which you have seen here. There is no need for that. I won't read it also. I will just go through. All of you are perhaps aware now that our country has had always a national policy on nuclear programs. Actually, it started even before we got our independence. It was Dr. Homi Bhabha who planted the seeds of this program even before we got our independence. And right from our first Prime Minister, Pandit Ji, all the Prime Ministers have taken individual responsibility for our nuclear program, which shows the importance that the government has given to the various aspects of our national policy on nuclear programs. And that policy had different components and different subcomponents. And what is satisfying to us is that the last 2 days' deliberations have focused on some of the very core aspects of those programs. I will just glance through the basic aspects what really happened last 2 days. Primarily, in the context of the long-term plan that the country has for our economic growth, And taking into account the projected increased demand on energy and power, we have had a plan to establish, to highlight the increased role of nuclear programs, nuclear science and technology in meeting that objectives. And Dr. Tiwari yesterday spoke very well, objectively, based on data, how nuclear power fares well in comparison to not only the conventional sources, but also the reversible sources. And that was very important as an opening talk. And in this context, some of the current activities in the state-of-the-art frontier science also were highlighted by Dr. S.V.G. Menon, Dr. Ryan Kumar, Dr. Bhakt Singh, Dr. R.V. Vishwanath. They included activities on fusion technology, accelerators, application of artificial intelligence, and rare earths. They were all very core aspects. And the current status of work on specific aspects like isotope separation and heavy water production was considered by Dr. Bhaskaran Mundayur. As regards application of nuclear technology in non-energy segment, there were presentations on the application of the fields of medicine and agriculture. The chief guest, Dr. Bhaskaran Pillai himself, touched on the topic of medical application. And Dr. M.K. Ray, Dr. K.N.S. Nair talked about radiopharmaceuticals and medical cyclotron, whereas Dr. Susan Epen, I think she has gone, talked about mutation breeding and food preservation. While highlighting all these beneficiary aspects, the importance of looking at the safety aspects has also been highlighted. Dr. Haridas talked about the myths and realities related to potential hazards and measures of nuclear safety. Dr. P.M. Ravi, on behalf of Dr. M.R. Iyer, talked particularly about the possibility of some of the technological jargon, the ALARA, the concepts, that kind of thing, particularly the linear, non-threshold approach, the problems involved in that kind of expressions, it was highlighted. Similarly, management and useful reuse of nuclear waste, there was a very important aspect. Useful sense of nuclear waste is described by Dr. Mustafa, and Dr. Tiwari and Dr. Malhotra also touched upon these aspects. In conclusion, and waste management that particularly Dr. Ray was talking about this morning, it's a core aspect. Unlike many conventional industry, the safety and core aspects are an integral part of atomic energy, nuclear aspect, right from conceiving, designing, and implementation. And in conclusion, a special mention must be made about the forceful presentation by Dr. Malhotra yesterday, who addressed specific issues of public concern and gave objective and assertive responses to those concerns. And Dr. Mittal also talked in the same strain and illustrated the role of INS in this capacity. And at the end, what is the take-home message of last 2 days' deliberations? I would say that there are two aspects. Number one, establishing that in the part of the objective planning for our national economic growth, the increased role of nuclear power and the safety, waste management, and peaceful applications. And I would also say that the last session was so enlightening. Students, whatever numbers are remaining now, you must go back with the message that nuclear power is an appropriate, clean, viable, cost-effective, and safe method of power generation, which is essential and unavoidable and integral to the future plans of the country. I will only say that you must keep your minds open by quoting 2 lines from Rigveda, Ano Bhadraha Kratavo Yantu Vishwataha. Keep your windows of information open. Let knowledge, let noble thoughts, not positive ideas, let objectivities come to your mind. Thank you.
Thank you, sir, for your comprehensive overview of this
And I must also say that on behalf of AER, we are so very happy so very satisfied for having collaborated with Sree Krishna College, where there was such a positive environment, not only from Dr. Vishnu and his colleagues, apart from the principal leading it and your student. We are so very happy for this event.
Thank you, sir. To conclude this ceremony, I invite Dr. K.V. Das, Vice President AERA, to propose the vote of thanks.
Dr. Vijay, Principal, our Chief Guest, Dr. Damodaran, Dr. R.K. Rajesh, Dr. Muralidharan, Dr. Muralidharan, and our distinguished guests, friends, and students of this college and other universities, and others, distinguished people in the audience. My duty is to propose a vote of thanks, but I find whomsoever I had to give vote of thanks, they are not here, available now. Most of the people have left. Anyway, I will do my duty. Coming back to the vote of thanks, allow me to extend our gratitude and thanks to all the delegates who participated in the seminar. With their presence, they made the seminar a great success and meaningful. We had the pleasure of conducting similar seminars few times before, but the cooperation extended by Sree Krishna College and the Guruvayur Devasam management was exceptional and gave us a wonderful experience. To conduct a seminar, we need a proper place, and along with necessary infrastructure, this college is managed by Guruvayur Devasam. Dr. Vijayan, BK Chairman, Guruvayur Devasam, and other members gave us everything we asked for. So I express our gratitude and thanks to Dr. Vijayan and the management. Dr. Vijay, Principal, Sree Krishna College, and the faculty extended all the help for the success of this seminar. I express my sincere and heartfelt thanks to Dr. Vijay, Dr. Rajesh, and members of the faculty. I have a special mention about Dr. Vishnu R., our convener. His enthusiasm was infectious and gave inspiration to all of us. Without his dedication, this effort could not have been so successful. I extend a warm thanks to him on behalf of AERA. Indian Nuclear Society is the main sponsor of this event. As you know, an event of this magnitude cannot be carried out without sponsorship. We are all retirees and our association does not have any specific income or assets to fall back on. So our target of spreading awareness about our nuclear programs can be done only with the support of INS. And many senior members of INS came all the way from different parts of India to encourage our efforts. I thank Dr. Jagtap, President INS, Dr. Mittal GD, Secretary INS, and Sri S.K. Malhotra INS, and other members of the Executive Committee for their wholehearted support and seek their continued sponsorship. Though Dr. Praveen Kumar and Dr. Govundangutti are AERA members, they did an excellent job as joint conveners. On behalf of AERA, I thank them profusely. There was a student session towards the end of our second day. I thank each student for their participation and worthwhile discussions. Coming to our chief guest, we all know that the credentials of Dr. Pillai KB need not elaborate on that. I think he was readily agreed to attend the inaugural session and to be our chief guest. On behalf of AERA, I extend our heartfelt gratitude and thanks to him. There were many excellent and renowned personalities who shared their technical knowledge with us. They are Dr. Raghavendra Tiwari, Sri S.K. Malhotra, Dr. S.V.J. Menon, Dr. M.M. Mustafa, Dr. A. Rain Kumar, Dr. M.R. Iyer. Instead of that, Dr. P.M. Devi represented him, and Dr. G.D. Mittal, Sri M.K. Ray, Sri Bhakt Singh, Sri K.N.S. Nair, and Sri Bhaskaran, Sri Anand Gangadharan, Mr. G. Haridas, Sri R. Vishwanath, and Dr. Susan Eapen. We all got benefited by the information they passed on and are extremely grateful and thankful to them. There were few more sponsors. A sizable amount came from Molecular Cyclotrons Private Limited, Kochi. I thank that group on behalf of the organizing committee. Indian Rare Earths Limited also promised to support financially. We owe a big thanks to them too. We had a very interactive session with the press on the 18th March 2025. On behalf of the organizing committee, I thank all the media for their participation and support. I also take this opportunity to congratulate the President, Dr. Surendranath Kaimal, the Secretary, Sri K.K.P. Nair, the Treasurer, Sri Vishambaran, and members of Managing Committee of AERA and members of the Awareness Committee for an excellent and dedicated effort to make the seminar a success. If I left out anybody, no, before that, I had to give special thanks to Dr. Darshana for excellent comparing, Miss Aditya, Miss Meera, and Dr. Manu for the coordination. Thank you so much.
One minute. Just now, Das mentioned about the comparing people. 3 people were here. They have done exceedingly better job. We would like to honor them. I like to request Meera Ullanatil to come and collect a memento from our president. Now I request Aditya PV to come forward and collect your memento. I now request Dr. Darshana PV, Assistant Professor, Department of Physics, to come and collect your memento. Thank you very much.
National Anthem. जनगणमन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय जय जय